I for a lock. O for a key.
सर नमस्कार।
चाहते नहीं गरम पानी फेंकती हूँ उसमें।
ଆଜ୍ଞା। I think we can start now. Professor sir.
Good morning. On behalf of organized committee, I welcome you to all in today's program of AFM 2020. I request Shweta Padma Madam to start the program.
A very good morning, ladies and gentlemen. Present over here, Honorable Vice Chancellor of KIIT deemed to be University, Professor Dr. Hrishikesh Mohanty.
Thank you.
Pro Vice Chancellor KIIT deemed to be University, Professor Dr. Sasmita Samanta. Dean School of Applied Sciences, Professor Dr. Pushpalata Bhattajoshi. My dear colleagues and all the esteemed delegates. Myself, Dr. Shweta Padma Praraj, and I'm very happy to welcome you all to the inaugural session of the International Conference on Advanced Functional Materials 2020 on virtual platform. Now, ladies and gentlemen, over these 2 days, you will have a wonderful experience of some brainstorming and informative technical lectures on a diversity of functional materials and the devices. I'm glad to share that participants all over the globe, they have joined this conference in the previous day, that is the pre-conference workshop, and we also expect a huge audience today. Now, such a mega event will give you an exposure of a diverse range of frontier materials on a common platform, and it will definitely infuse a spark in the young minds, and they will be encouraged to apply them in some applications. So with this, now I request our Dean, School of Applied Sciences, Professor Dr. Pushpalata Bhattajoshi, to deliver her welcome address. Ma'am, please.
Thank you, Shweta Padma Madam. A very good morning to all. Respected chairs of the inaugural session of International Conference on Advanced Functional Materials, AFM 2020. Honorable Vice Chancellor, Sir. Honorable Pro Vice Chancellor of KIIT University. The convener, Professor S.K. Parashar. Coordinator of Physics, Dr. D.R. Raut. And the entire organizing team of AFM 2020, all invited speakers, delegates, colleagues, students, ladies and gentlemen. We cordially extend a warm welcome to you all to this international conference this morning. The objective of this conference is to bring together the academia, R&D stalwarts, policymakers, industry representatives, young students, and enthusiastic public on a common platform for stimulating discussions on advanced functional materials when they are touching our lives throughout our everyday life, through pharmaceuticals, energy, healthcare, automobile, chemical, aerospace, building and construction, and many more. To tell some examples how they touch our lives, everyday lives, I was reading a journal today, some glimpses from that. scientists at the Department of Energies of Argonne National Laboratory, they have developed a light activated coating for filtration membranes, the kind used in water treatment facilities, at semiconductor manufacturing sites, and within the food and beverage industry to make them self-cleaning, which eliminates the need to shut down systems down in order to repair them. In another example, Jonathan, an associate professor in mechanical engineering, they have developed an aircraft thermal management technology that stands ready for adaptation into other areas. This will allow one-way heat transfer of a breathing droplet diode, enabling smart thermal management of electronics, aircraft, and spacecraft. In another example, nature's blueprint for the human limb is a carefully layered structure with stiff bone wrapped in layers of different soft tissue like muscles and skin, all bound to each other perfectly. Achieving this kind of sophistication using synthetic materials to build biologically inspired robot parts or multi-component complex machines has been an engineering challenge. By tweaking the chemistry of a single polymer, researchers have created a whole family of synthetic materials that range in texture from ultra soft to extremely rigid. The researchers has claimed that their materials are 3D printable, self-healing, recyclable, and they naturally adhere to each other in air or even in underwater. So these are few examples starting from the domestic water filtration systems to aircraft to biological parts that makes our everyday life very functional, effective, and progressive using advanced functional materials. The examples are really plenty. If we look into the industry value chain, starting from upstream raw material suppliers to measure downstream buyers, or even we look at the industry market types, starting from ceramics to energy materials to nanomaterials to composite or similar, we see major challenges and opportunities to spearhead our R&D agenda, cutting across traditional and emerging disciplines to solve various needs of humanity. In this context, drawing attention of all stakeholders through such conferences is the right step taken by the conveners. We are grateful to the visionary leaders of KIIT University, led by the Honorable Founder, Professor Dr. Achyutananda Samanta sir, the strategic directions given by the Honorable Vice Chancellor Sir Professor Mahanti, Honorable Pro Vice Chancellor Madam Professor Sasmita Samanta, Honorable Registrar Dr. Gyana Ranjan Mahanti, for envisioning these challenges, encouraging and supporting us to respond to the demands of time. Once again, we welcome all directly or indirectly associated with the event to experience intellectually stimulating discussions. We extend our sincere gratitude to the honorable chairs of the session, all invited speakers, delegates for their vibrant presence and participation. We sincerely look forward to a successful event. Thank you.
Thank you, ma'am, for your welcome remarks. Now, I take the privilege of inviting our Vice Chancellor, KIIT deemed to be University, Professor Dr. Hrishikesh Mohanty, to grace the occasion with his valuable words. Sir, please.
Dr. Satyapadma, good morning to all of you. Honorable all the dignitaries, the speakers, participants of the conference, all the researchers from different institutes for India and abroad. I, on behalf of the university, welcome all of you to this conference. And our esteemed Dean Madam, Professor Pushpalata, and our esteemed Pro Vice Chancellor, Professor Sasmita Samanta, and all the department coordinators, Professor Parashar, and the organizers of this conference. I would like to thank all of you for organizing such a massive conference along with a workshop, pre-conference workshop, that which is very essential for training the new researchers in this field. I am sure you all must be very excited to listen to the very honorable our speakers, invited speakers, and the young researchers, their works. Dean Madam has already told about the importance of this area, and in today's world, how important these functional materials are. This is not my area of research, so I don't want to tell more about it, what she has told. At least I know that this material science research is so important. When I was doing PhD, that time itself, the IIT started the material science centers. So since almost like 35 years back. So since then, this research in material science is still very, very exciting, and still it is a hot topic to pursue research, because many applications, they depend on new materials, different kinds of materials, with different properties. So as you have a complex applications, we also need a very, very specialized materials. It is something like, it reminds me from epic of Vishwamitra making a new heaven. It's its own world. So these material scientists, it looks like they want to make their own world, which is something more than what the natural world has given with the elements. So this is of course a risky business, because you are competing with God, competing with the nature, but also it is a reality that we need a lot of different kinds of materials, and the country which is good in this research does the best in its economy, because it directly adds to the economy. Long back, I think last year, I believe Professor Bhattacharjee from UK came, who heads a specialized center on this, the material designs. After later, he has gone to the designs, also on the materials. So this area of research being so vital, and I am happy that School of Applied Science is also very much engaged in this area, and this research particularly is very, very essential when our nation is looking towards Atmanirbhar, what the Honorable Prime Minister gives a call, is that self-reliant in everything. And in this research in the material science, really will have a lot of contributions towards that if we can get new materials, we can synthesize new materials, we can at least stop importing some materials. That will be so good. And this innovation has been into the norms, into the blood, into the workings, into the thinkings of this university. As Dean Madam told that no, the honorable founder of this university has a noble intention of creating a knowledge hub, which is recently been recognized by the government of India, giving the best innovation award to KIIT University, and that is a signature of his noble intention, and that is where the teachers, researchers of the universities are engaged in. And in that sense, the applied science school does its humble bits towards the innovation. I know that the school, all the different areas they are engaged, and I would like to make a request today. Those honorable speakers, those who are here, they, after pandemic, they are all welcome to the university, to this young university. They welcome you, and we would like to, our researchers would like to interact with you, and we'll learn from you, and we'll collaborate with you in their research work. And the organizers, I was looking at it so professionally. This event is organized. I'm really very happy for this pre-conference workshop. And here goes with the real intention of the conference. The conference is just not really, not only presenting the papers of your researchers, but also it has a responsibility to train the new researchers in this field. So in that sense, this workshop has really put its effort. I'll congratulate the department, the organizers, and also Professor Parasar for taking this lead. And I wish this event becomes successful, and this also becomes an annual event to showcase the research in this area the KIIT University is engaged in. Wishing you all the best and have a good time in the conference. Jai Hind. Thank you.
Thank you, sir, for encouraging our participants. After this, we had the address of our Pro Vice Chancellor, ma'am, but due to some unavoidable reasons, she will join after 15 to 20 minutes. So may I now request Professor Dr. Dibyaranjan Raut, Associate Professor and Coordinator, Department of Physics, School of Applied Sciences, to present a brief profile of our department and the vote of thanks. Kindly bear with us. Sir, please.
Good morning to all. Honorable Vice Chancellor Professor Hrusikesh Mohanty sir, Honorable Pro Vice Chancellor Professor Sasmita Samant ma'am, respected Dean School of Applied Science Professor Pushpalata Pattojoshi ma'am, all the participants, honorable dignitaries, distinguished guests, my friends, colleagues, and the research scholars and MSc students participated in this conference, registered for this conference. On behalf of Department of Physics, School of Applied Sciences, and the organizing committee of AFM 2020. I, Dr. Divyaranjan Raut, the coordinator of physics and the co-convener of AFM 2020, feel immense pleasure to take this opportunity to propose the vote of thanks. And prior to that, I'll speak few words about our department and school. In our department, the strength is our faculty members. We have 17 faculty members. They are from different premier institutes, some of them from IIT Madras, sorry, IIT, different IITs, IIT Madras, IIT Delhi, IIT Kharagpur, and some of them are from NITs, NIT, particularly NIT Raulkela, NIT Durgapur, and some of them from IIC Bangalore. So it's a bunch of intellectuals from premier institutes, and also we have very experienced faculty members, those who have served around 20 to 25 years in teaching and research, and some of them have experience in postdoctoral experience in abroad, and half of the faculty members are newly joined, so they are very enthusiastic and active in current research. In our department, we have run BTech program, particularly general physics for first year BTech students, and some open elective courses for higher semester BTech students. Then we have run MSc program. Uh, mm, Last 2 years we have started, and the feedback from the students from the this year's registration for admission and all, it is very encouraging. And we have a vibrant PhD program already in our, from our department. We have awarded around 20 to 25 students, and including this year's PhD awarded list, it will be reaching 30 students are awarded from our department. And in our department, we have done around 20 funded projects from different funding agencies of Government of India, and we have completed, and now it's around 5 to 6 mega projects are running. So if altogether, it is around 500 lakhs funded projects are running in our department. We have a lot of international collaboration with along with our ITs, NITs, and most of our faculty members, they have working in interdisciplinary work. As Vice Chancellor sir told, material in our department, most of the faculty members are working in a different materials. Some of them are working in functional materials with different applications. Some of them are working for solar cell applications, photocatalysis applications, and so on. So, as a whole, our department will have uh, very high scope for research, particularly interdisciplinary research, uh, along with some theoretical researchers are there. We are collaborating. So not only with the experiment, we are also collaborating with the theoretical persons. So to design the models, and so I welcome all the participants who are interested to collaborate. We are always open to them. We can collaborate to have some confidence, because though we have achieved institute of eminence, still we are tagged as private university. So don't go with the word private university, rather you go through our profiles, our credentials, and you will feel that our we can you can see our strength, our quality of publications, number of publications. So seeing those credentials, you can I am sure you will feel to collaborate with us, and we are always welcome you to collaborate with all the participants, the research scholars who are present in this conference. Now I'll, with these few words about our department, our school also, we have chemistry, mathematics. In chemistry also, we have large, around 20 to 25 number of funded projects are running, and most of the faculty members are involved in active research, starting from the organic, inorganic, physical chemistry, and many of them are interdisciplinary, and they are working for drug design, drug development, and also they have collaboration with biotechnology, and they are going for medical applications. Similarly, and some of our colleagues in chemistry, they are working for environmental science, particularly on water. So we have a very good lab for water analysis, and so anyone is we can come and do the use the water analysis lab. It is a full-fledged lab. Then also we have many faculties in mathematics. They are involved active research, particularly on environmental science. They have designing the models, and we have a strong collaboration with them. So with this brief introduction, now I'll go for vote of thanks. We are thankful and obliged to our honorable founder, Professor Achyutananda Samant, for providing us such a huge platform and guiding and motivating us in each and every day, in each and every occasion, to improve and to excel. With his vision and our hard work and dedication, we have reached at the top. Now we are at the top. We got the Institute of Eminence. Now it is our duty and responsibility to maintain the position at the top, and we express our heartfelt gratitude to our Vice Chancellor Sir, to our Pro Vice Chancellor Madam, to our Registered Sir for their constant support and encouragement to improve the quality of teaching, to improve the quality of research and number in the campus. And we are extremely grateful for them, for they could spare little time from their busy schedule and motivate the young researcher, our faculty members, with their enlightening words of wisdom. Thank you, sir. Thank you, ma'am. Wholeheartedly, we'll try our best to match up with your expectations and your belief to see our university at the top. Further, we extend our heartiest thanks to our Dean Madam for her guidance and support during the course of preparation of this conference. Not only for this conference, each and every event that we organize in our department, in our school, she always support us, she always guide us, and but meticulously each and every step she used to see how the things will put in proper place. Thank you, ma'am, for your support. We have been fortunate to have some of the eminent persons from academia, industry and utility working in a functional materials lab. They have come and registered for this conference AFM 2020. We express our sincere gratitude to them. I am sure the participants will be benefited by attending the conference. We are thankful to our invited speakers, those who have presented yesterday. and also the young researchers, those who have actively, very enthusiastically present their work till 8 p.m. Evening. So we really from our heart express our heartfelt thanks to their patience. Um, then we have also thankful to our publication cell, our media, and the ICT cell and the support staff for their constant support and timely support so that we could organize this event. Finally, my heartfelt regards to the organizing convener, Professor Parasar, co-convener Dr. Bhavya Bhushan, and the technical committee and the session chairs, Professor Alok Patnaik, Professor R.N. Mukherjee, Dr. Shwetapadma Praharaj, Dr. Vidibhushan Sahu, Dr. Sushant Kumar Sahu, Dr. Lalatendu Biswal, Dr. Maya Devi, Dr. Priyadarshini Parida, Dr. Jasasri Roy, Dr. Jasaswini Tripathi. Wholeheartedly, I would like to thank on behalf of our department, the digital team of our school, of our department. Because of them, we could organize this conference. Because of their hard work and effort, it is possible for us to organize this conference in virtual platform where 16,000 participants are there across the globe. Dr. Gopal Pradhan, Dr. Sutanu Mangal, and Dr. Garkisa. Thank you, sir, for your hard work and effort. I know you have spent a few sleepless nights, so we really oblige for you people. Then together we'll make this conference a good success. Thank you. Jai Jagannath.
Well, that was a very good description of our department. Thank you, sir. With this, we end our inaugural session. I'm very sorry to say that with a very busy schedule, Pro VC ma'am, she could not join the inaugural session.
Very good morning.
Yeah, sir. So we are just ending the inaugural session now. We'll just proceed towards technical sessions. So I please request Dr. S.K. Parasar, convener of AFM 2020, to just introduce the session chair, Professor Dr. Anil Chobe. Sir, please. Parasar, sir, please introduce our session chair.
Today's session chair is our materials head, and Dr. Anil Chobe from IMT. And it is a warm welcome to our Professor Sahu Thomas, Vice Chancellor of KIIT. Very nice to see you. So good morning, sir. Good morning. Sahu Thomas, sir. So I request Anil Chobe, sir, to start the session. बोलिए हम बोल दे क्या बोल दीजिए ना बोल दे क्या
Hello, actually this was not unmuted, so I could not able, just now it is unmuted, I think. So I am audible to all of you. Yeah, myself Anil Kumar Chobe from IMMT, Institute of Minerals Fertilizers. Yes, sir. Dr. Parasar, whether I am audible to all of you?
Yes, sir. Yes, sir, you are audible.
Okay. Thank you, Dr. Parasar, for your nice introduction. So, actually, this session is first talk is by Professor Sahu Thomas. So I'm going to just brief about Professor Sahu Thomas. Professor Sahu Thomas is a Vice Chancellor of Mahatma Gandhi University, Kottayam, Kerala, India. Apart from his as a Vice Chancellor, he is also having a vast experience, and also he is associated as a Professor of Polymer Science and Engineering School of Chemical Science, and also a founder director of International and Inter-University Center of Nanoscience and Nanotechnology, Mahatma Gandhi University. And apart from this, he is having very huge experience in the field of polymer and composites. He is actually having a lot of experience in different capacity at a different post he has handled during his career. So, and his major scientific contribution in the area of the polymer blends, basically miscibility, phase separation, crystallization of polymer blend, morphology, mechanical property, etc. And he is also having a lot of experience in the area of the fiber field, polymer composites, short, natural, synthetic fibers, field thermoplastics, thermoster, rubber, polymer, rubber, interfacial adhesion, fiber surface modification, etc. Also having a vast experience in the area of particular field polymer composite, aging and degradation of the polymer composites, pre-vaporization phenomena, absorption and diffusion in the case of the polymer, and interpretation polymer system, recyclability and reusability of waste plastics and rubbers, elastomers, cross-linking, double network in elastomers, synthesis and accelerator, vulcanization, dual porous nanocomposites, scaffolds, and tissue engineering in the field of biomedical application as well. Polymer nanocomposite, he has a lot of work, and he has several publication in this area. So he has, apart from this, he has several awards and honors in his credit. So it is not able to tell all the, but I'm going to tell some of the awards on his credit. As in University of Lava postdoctoral fellowship, he has carried out in 1989 to 1991. He is also a fellow of Royal Society of Chemistry, London, chartered chemist in 2000, and he is also having a visiting fellowship of the Catholic University, Belgium, and he is also having many distinguished fellowship award of the Joseph Stephen Institute, Slovenia in 2010. He has also a fellow of Royal Society Chemistry, London from 2012, and he has awarded Bronze Medal of Chemical Research Society of India in 2013, awarded Material Research Society of India Award in 2013 as well, and he has also awarded the Society of Educational Scientific Research Nano Tech Science Award in 2014. So apart from this, he has guided many students as a PhD, postdoctoral, and also many other category. So he has more than 75 PhD students he has guided in his career, and he has completed around more than 20 to 30 projects funded by different agencies. And he has also completed different international projects on his career. So with this short biodata, I'm going to invite Professor Sahu Thomas for his lecture. Actually, he is going to talk on this interfacial modification in nanocomposite to a tailored functionalities. So I invite Professor Thomas for this lecture. Professor, please.
Thank you. Thank you. Can you all hear me?
Yes, please go ahead.
Very good morning to all of you, and thank you, Professor Anil, for the kind words of introduction. Congratulations to organizers. Congratulations to the wonderful conference. All my good friends, faculty members, students. I'm really excited to be with you today. And my title of my presentation is Interfacial Modification of Nanocomposites to Tailor Functionalities, ultimately to how to transfer these materials into functional materials for various applications. Application space, application in agriculture, application in health, wide range of application I'm going to cover today. If you look at the outline of my presentation, I will all take you to the field of nanomaterials by showing a few slides. Then I will show you our work on clay and polymer, nano clay and polymer. And we applied this for tire engineering, working with Apollo tires. Then I will bring you to our work on CNT material, carbon nanotube, polymer composites, hybrid nanocomposites with General Cables, the biggest cable company in the United States. We cooperated with them. Then I will talk to you about super tough materials with ISRO, some work on sensors if time permits. Then I will come to bio nanocomposites and tissue engineering and concluding remarks. See, my group is active in a variety of nanomaterials, graphene, CNT, kaolinites, metal oxides. We work on a variety of nanostructures, pose, nanocellulose, nanochitin. And what we do is we make all these nanomaterials in my laboratory and put into polymers to make polymer nanocomposites. You might ask, what is the importance of this? When you mix polymers with nanomaterials, you can make wonderful structures, functional materials. You get very good reinforcement, very good strength, very good modulus, without sacrificing ductility. Excellent optical properties, excellent electronic properties, heat stability, flame resistance. You could achieve lots of wonderful properties. But when you look at these nanoscopic fillers, nanoscopic material, you can classify them based on their aspect ratio 1, intermediate aspect ratio 10 to 20, high aspect ratio. You put them into polymers, you know what will happen? Viscosity will increase. Viscosity means resistance to flow. When you put this nanofillers into polymers by melt mixing or solution casting, the viscosity will increase. Industry people doesn't like it. You know why? Because high viscosity means high processing cost. So if you look at the viscosity buildup, the high aspect ratio fillers like carbon nanotube graphene, they raise very high viscosity. That's a very big issue that we have to sort it out. If you look at the mechanical reinforcement, look at high aspect ratio fillers are good. Graphene is a good material. Nanocellulose is an excellent material. But if you look at spherical particles, they are also good, but not as good as high aspect ratio filler. Look at barrier. We have several collaborations with many companies, especially tire companies, to make inner tubes in the liner for automotive tires. Where also they like clay, because clay has very high resistance to transport, gas transport. In terms of dispersion, there's another important issue. When you try to disperse them in polymer, suppose your dispersion is very bad, then you don't get any good properties. So high aspect ratio fillers are very difficult to be dispersed. So I request my colleagues, when you work on nanomaterials with polymers, please consider all these points very carefully. Now let me tell you our work on clay. Clay is an exciting material. Look at the stiffness of clay, 170 gigapascal. It's a very interesting material. Polymer modulus is something like 2 or 3 gigapascal. So when you mix polymer with clay, you can make strong material. And the chemist will say the structure of MMD is TOT, 2 tetrahedral fusion octahedral. And the gallery spacing is very small, less than a nanometer. So they are all held together by electrostatic force of attraction. Look at this. You can see the picture of clay here. They're all held together by very strong electrostatic interaction. And I am mixing with the polymer. Polymer is a macromolecule. And if the mixing is bad, you know what happens? You end up in a conventional composite. You don't achieve anything. If you get very good dispersion, we call exfoliated nanocomposites. All the particles have been separated. And this is something intermediate. It's called intercalated nanocomposites. So how do you find this? You know, my PhD students always do X-ray and see whether it is intercalated or exfoliated or conventional material. We also do a lot of microscopy, high resolution TEM, SEM, etc. My group is also very active to bridge between the polymer and mineral surface. You know, polymer is like polypropylene, polyethylene, natural rubber, SBR rubber, they're all hydrophobic. But MMT is extremely hydrophilic, so there is a mismatch, hydrophilic, hydrophobic mismatch. So we have to use compatibilizers. We have to use surface active agents. We have to apply good chemistry to make a strong interface. So I will tell you, we use lots of compatibilizing agents to connect clay and polymer together. That's extremely important. And you see, there are a variety of compatibilizing agents. The reaction is very similar to action of soap in oil water. When you add a little bit of soap in oil water mixer, you get a fantastic dispersion. Similarly, if you use amino acids, alkylamines, silanes, you can get wonderful interaction between polymer and the nanofillets. I have a beautiful cartoon here. You can all see the clay. This is our surfactant. We treat clay with surfactant. You see the surfactant go and sit inside the clay. And what happens? The gallery space is increased. Once the gallery spacing is increased, the polymer can mix with the clay beautifully. I can show you another nice picture of my student, work of my student. The first one is the neat clay. You can see this is a neat clay. The gallery spacing is very low. And the student has mixed this clay with a different type of surfactants, treated with different types of surfactants, so very molecular weight. Look at the peak is shifted to lower angles. What it implies? You are increasing the gallery spacing. So this is one of the first steps we do. You treat the clay with best surfactant and increase the gallery spacing. And this you can monitor by X-ray scattering. We can also look at transmission electron microscopy. I will show you some work we did a couple of years ago. I had an Indo-French program. Dr. Couloud came from France, and we did some nice work. I will show you what Couloud did. Couloud, from a French student, came to my laboratory. She came with clay. Look at this. She did two types of manufacturing process, preparation process. One, she directly went for polymerization annealing on the surface of this clay. You know what we got? We got intercalated structure. We could not separate out the clay platelets. Dr. Couloud did another beautiful chemistry. She modified the clay surface with a difilm disonium cation, a very simple chemistry, and then went for polymerization. Look at what we got, completely exfoliated material. And the conductivity of this is 5 times higher than this one. Modulus of this is 10 times higher than this. See, we made excellent material. Very small chemistry could make dramatic changes. Let me show you our work with Apollo and MRF. Lots of people worked with me. I've shown the picture of Apollo people, MRF people, and my PhD students. Look at 2 pieces of rubber. One piece of rubber is combined with the big fillets, conventional fillets. On the right-hand side, you see rubber mixed with clay. Once you fix rubber mixed with clay, you know what happens? The incoming gas molecule. Usually in the tire, we fill nitrogen now. Once you have a beautiful inner tube or inner liner with this sort of compound, this nitrogen molecule cannot escape. A very complicated diffusion profile. I will show you a beautiful result we got. This is pure natural rubber. The first one is pure natural rubber. The air will escape very rapidly. And the bentonite, just 5% of bentonite in natural rubber, 5% of fluorohexoride in natural rubber. The natural rubber became completely impermeable, almost impermeable. Fluorohexoride was the best. You see how we organize the platelets in the natural rubber matrix, beautiful orientation of the platelets. Now I will show you some of our work with SBR rubber. SBR is a very important synthetic rubber. You can see the photograph of Dr. Gigi and my collaborator from engineering college, Dr. Soni C. George. You know what we did? We bought rubber from a company, synthetic rubber, and we made use of carbon nanotube. You know what my PhD student did? If you mix rubber and carbon nanotube directly, you cannot mix because they don't like each other. Additionally, carbon nanotube from bundles. You know what my PhD student did? She made use of ionic liquid. When you use ionic liquid, you know what happens? Carbon nanotube is well disposed in SBR matrix. If you don't use an ionic liquid, look at clusters of carbon nanotube. And eventually what, Gigi did, look at this slide. Conductivity as a function of carbon nanotube. You see a beautiful percolation process. Look at this curve. And we made excellent EMI shielders, flexible EMI shielders for electromagnetic machineries, electronic machineries, mobile phones, TVs. We made beautiful EMI shielders. And you see the shielding effectiveness, we got something like 45 dB. This is the shielding effectiveness we got. Let me show you something we did with carbon nanotube, with rubber, natural rubber. See, this is a very interesting slide. What you see is stiffness as a function of strain. Natural rubber filled with the carbon nanotube. This is neat rubber. You get a linear viscoelasticity effect. Stiffness as a function of strain. You're stretching the rubber. 1% of carbon nanotube, again very close to linear viscoelastic effect. But what happens when you put 5.4%, 8% of carbon nanotube in natural rubber? You get a beautiful nonlinear viscoelastic effect. What is the reason? Because when you put 5.4% of carbon nanotube in natural rubber, carbon nanotube forms a network in natural rubber. And when you stretch the rubber, the network is destroyed progressively. That is why you have a decrease of stiffness. You know, ultimately what we did, we had a cooperation with an artificial skin company in France, and they were interested in flexible conductive rubbers. I request all of you to look at this picture. Volume resistivity as a function of CNT. You see, volume resistivity decreases dramatically. That means conductivity increases. So we made flexible, elastic, conductive, rubbery material by putting carbon nanotube in natural rubber. Let me show you another slide, another work. The PhD student was Jasmine. She became an assistant professor now. We had a cooperation with the General Cables United States, the biggest cable company in the US. And the US company sent us a lot of materials. And the material we have used, polymer we have used is XLPE, cross-linkable polyethylene. And you can see the first slide where we have my PhD student mixed aluminum oxide with XLPE. You can see clusters of aluminum oxide. This is clay and XLPE. Look at this. We got a good dispersion. One interesting thing I want to show you, see when you mix them together, clay and aluminum oxide together, I'm putting into the material. See?
It's 10 hours.
Combination of two materials in a polymer matrix. They self-assemble, forming a network. So we got fantastic results. I can show you the next slide. You see, this company was interested in high modulus material. If you look at this slide, you can see the combination gave excellent results. The modulus actually went up dramatically. Similarly, if you look at the diffusion profile, you know, underwater cables, you know what happens, water will diffuse. Look at the last slide. When you have the combination of clay and aluminum oxide, this cable compound was resistant to water. So we made excellent nano composites with this material. I will now show you some work on biomedical applications. Look at, I have a big biomedical group with me. We do a lot of electrospinning. Robin Agostini is in Qatar now. Gia has now joined KUSAT. Blasi is submitting thesis. Dr. Joshi is in China. Praveen has gone to Bangalore after a series of postdoc. What we are doing is we do electrospinning process. Look at our electrospinning setup. We make use of biocompatible polymers like PCl or PLA, and then we mix with nanoparticles, zinc oxide or titanium dioxide, variety of nanoparticles. Sometimes plant extract. We also work with Ayurvedic doctors. We put the extract of plant. And then we do electrospinning, and we make nonwoven fabric. Look at the internal structure of the fabric. They're all beautiful nanoscopic filaments. Look at the sacrificial wound we have made. This is sacrificial wound. And the wound is closed by this tape. You see, after 2 weeks, we made wonder, you know. No scar and the wound is completely closed. You might ask why? Because we have beautiful cell migration, cell proliferation, angiogenesis taking place, and your wonderful healing. We work with the guinea pigs because that's also integral part of it, because we have to do a lot of in vivo and in vitro studies. I will show you one slide. Here you can see the structure of our tape under electron microscope. You can see the nanoparticles we have incorporated. These are all zinc oxide. See? Zinc oxide has a very magnificent healing effect. The zinc oxide particles have been marked beautifully. And you can see this is PCl plastic, biocompatible polymer, and you have zinc oxide. While putting some zinc oxide, you have hydrogen peroxide evolution, and then the wound healing has become so efficient. You have excellent cell proliferation, cell migration, angiogenesis, and these lead to wonderful wound healing process. So my group is very active in developing wound healing nanocomposite materials. And interestingly, I want to tell you that, you know, after a while, all this nanocomposite has to disappear. You know, you put a tape, or you put an implant, or you put a scaffold in your body. After a couple of months, the scaffold has to disappear. Tissues have to grow. That is why we are using biocompatible polymers, biodegradable polymers. And we're putting 1% of nanoparticle. We've also found the biodegradation becomes faster. See, this composite with 1% nanoparticle, the degradation became faster. So by putting small amount of zinc oxide nanoparticle has two advantages. One is the healing became very fast. And second point is the biodegradation became extremely fast. And now I will show you the last part of my presentation. We are also working on bio-nanocomposites, extracting nanoparticles from nature, from agricultural residues, from agricultural waste. So my PhD students go to the agriculture plantation, collect the waste. It could be banana waste, it could be pineapple leaf, or it could be rice straw, it could be wheat straw, whatever be it. I have a lot of collaboration with Sweden and with many countries, Brazil. You can see the plant here, whatever be the plant, it could be banana, it could be pineapple, it could be oil palm, and we are able to make nanocellulose by a simple process. And this nanocellulose has lots of applications, photonics and composites. I wanted to show you the slide of Professor Alain Dufresne from France. Alain Dufresne is a world leader in making nano from agricultural residues. He is the best, #1 in the world. This is some of the photographs I'm showing from his work. You see, nano he has extracted from Tunisian cellulose. Nano extracted from wheat straw. Nano extracted from cotton. Nano extracted from crab shell of the crab, that is nanochitin. Nano extracted from waxy maize, the waste of the maize. So we are able to make nanoparticles from agro waste. I will show you a couple of slides, what we have done recently. This has come in ACS paper. Those who are really interested can look at the ACS publication. My PhD student made nanocellulose dispersion from banana waste. You see in this round bottom flask. And then what he did is he injected aniline into it. And then we went for a polymerization process, in situ polymerization of aniline. You know what we got? After vacuum filtration, we got very thin conductive paper. He went for a hot processing, and this is a paper he has made. Fantastic material, very conductive material. And application of this is for EMI shielding, electromagnetic interference shielding applications. Our mobile phones, we need it. Our radios, we need this EMI shielders. So he made exciting, tiny cellulose paper with different thicknesses, 0.75 mm, 1 mm, based on your requirement. I will show you another work which just recently published in carbohydrate polymers. Another student of mine, Avinash Pai, he made nanocellulose. He also followed the same route as Dibu. And then what he did is instead of vacuum filtration and molding, he went for a freeze drying process. And we made foams, beautiful foams we made. It's called aerogel, very lightweight material. And we also found that these lightweight material is also extremely beneficial as EMI shielders. So we are making lots of functional materials from agricultural waste. That's our starting point. And then you mix with, you do, in situ polymerization process, and we can make exciting material. Now, I have asked my PhD student to make transparent material, transparent EMI shielders. We need such material for transparent applications. So I'm going to conclude my lecture. I don't want to take much of your time. My group is extremely active in making different types of nanoparticles. Many of the nanoparticles we synthesize in our laboratory. We work intensively on nanoparticles based on plant resources. And we are able to make excellent barrier materials. Materials with really good stiffness, good mechanical strength. We are making EMI shielders for electromagnetic machines. We are making conductive rubbers which are elastic for artificial skin. We did not show anything about water purification. I have a big group on water purification using nanocellulose. Sensors, we are also able to make sensors and lots of biomedical applications, especially wound healing. So I am thankful to Professor Siena Rao for generous funding for the nano mission, support us very much. We have a transmission electron microscope in our laboratory because generous funding from Professor Rao in the nano mission. And we also got support from ISRO, CSIR, DBT. You can see we got support from all the funding agencies. Industrial funding from General Cables USA is acknowledged. Apollo Tire, MRFI is acknowledged. And you can see my collaborators in France, Germany, Brazil, Belgium, and my collaborator and my colleague in the nano lab. Right now, he is the director, Professor Kalarikel, and the hard work of all my students in the laboratory is well appreciated. You can see my group in chemistry. I have two groups. There's a group in chemistry. You can see the picture of, Yves Rochens. When he visited our laboratory, we took a photograph. And this is my group in nano. You can see the present director of nano science and nanotechnology, Dr. Nanda Kumar. And you can see we have international students from Malaysia. We have students from Africa. We have really nice international group. And this is our campus. Very welcome to our campus. We have beautiful sceneries in Kerala, ghost town country. We have beautiful canals. We have very old temples. We have houseboat. Then there's a traditional art of Kerala, Kathakali, Mohiniyattam. So very, very welcome to Kerala. And I'm also an editor of nanostructures and nano objects. Elsevier journal. This is a conventional traditional journal, not open access. To those who are really interested to submit your good paper, please submit. Now the site score, I was told that the site score is 5.6. We are organizing an international conference, 100 years of macromolecular science. Probably all of you know that the idea of macromolecular was introduced in 1920 by the German chemist, Professor Hermann Staudinger. He got Nobel Prize in 1953. So we are celebrating 100 years of the existence of macromolecular science. In the campus in November 11, 12, and 13, we are all welcome to this meeting. We're also planning a nano meeting next year. Probably this is a face-to-face meeting. The previous meeting, the 100 years of macromolecular science meeting is a webinar. And the nanomaterial conference will be a face-to-face meeting that is in April. I hope the pandemic might get over by that time. And thank you very much for your patient hearing. Thank you.
Thank you, Professor, for your giving a very excellent overview on this nano composite material and giving very insight view for this, making a composite for different applications like a functional materials applications as well as the biomedical applications. And I think you have given very excellently given the overview of your some of the work, which is a very high impact value. And I think most of us have taken off some of part of this. So and I am very much happy to see some of your work on this aluminum clay and XLP composite. So in this one, I have one doubt, sir, regarding this aluminum and clay. You saw that this mechanical property improving as you are adding more and more aluminum in this clay. So I would like to know what type of bonding between the clay and aluminum, which actually resulted the improvement of the mechanical property of this composite.
Very, very interesting question, Professor Anil. You know, it was a very surprise for us. When you put aluminum oxide alone, of course, we got an improvement of 50% or 75%. Clay also, we got a similar impact. When you mix them together, 2.5% of aluminum oxide, 2.5% of clay, when you mix them together, you put into XLP, the modulus is increased by a factor of 2 or 3, sometimes 4 times. You know why? Both the surfaces were modified. Both the surfaces, aluminum oxide has got alkyl group protruding out, clay has alkyl group protruding out. These alkyl groups came together. You know what happened what happened at the end? We got a beautiful network. We got a beautiful network. That network is the reason for we got such an increase in modulus, because we got excellent network. Look at this picture. See this picture. This is clay and this aluminum oxide. Look at the network formed inside the polymer matrix. And this network immobilized the polymer chains. The polymer chains cannot move. Their mobility is restricted. And as a result of this, it's a big jump in modulus. Very interesting question. And the chemistry, I did not show, the chemistry has been formed by infrared. Because the alkyl group protruding from the clay, the alkyl group protruding from the aluminum oxide, they like. Because of that, there's a beautiful network. Very brilliant question. Thank you, Professor Anil.
Yes, this XLP helps to forming the network of this inside the clay matrix.
No, actually the XLP is the matrix, polymer matrix, the surface groups on the filler, the chemistry on the filler surface, that really is responsible for this network. Yes, yes.
And how the interface between the clay and this alumina play a role in this one?
Fantastic interface. You know, the interface is fantastic. Because the clay is also modified. The gallery space in the clay was very much high. And when you do this, then you have 50-50, 50% of clay, 50% aluminum oxide. You know, the clay stacking, aluminum oxide clustering, look at this clusters of aluminum oxide, that is completely prevented. So this sort of mixing two fillers together will enable excellent dispersion and excellent network.
Yes, okay. So now the session open for any question or any doubt. So please raise hand who want to ask any questions on this topic. So anyone having any doubts on or any clarifications or any comments on this?
So there are a few questions typed in the chat box. Maybe can I read it?
Yeah, please.
Okay, so someone, Afsarin Khan has asked a question. Can we use these nanoparticles to make protein RNA-based biosensors for cancer diagnosis? If yes, please suggest some nanoparticles.
You see, my group under leadership of Professor Nanda Kumar is using nanoparticle for imaging applications. We use quite a lot of nanoparticle in imaging for cancer. We also use nanoparticle assisted drug delivery. We finished one PhD. You know, so a student of mine connected AIDS capsules, drug to a nanoparticle. A nanoparticle was biocompatible. And then we could do drug delivery. So nanoparticles can make lots of applications in medicine. So we have a big group on that area. I did not show you any work on nanoparticle assisted drug delivery, nanoparticle assisted imaging. These are all very important field. So we have PhD program going on in this area, and we are very happy to cooperate also with you.
Okay, so there is one more question typed in the chat box from Shruti ST.
Yes.
The question is, if epoxy polymer is used as a host matrix, will there be interaction between inorganic salt like cobalt chloride and epoxy, or epoxy will be just a binder?
You see, if you want to have some interaction with epoxy, we worked with epoxy quite a lot. I did not show you today. If you want to have some interaction with epoxy, you have to modify this filler surface. You have to modify some epoxy group, or you have to modify some functionalities. Therefore, these epoxy groups can interact. It could be hydrogen bonding interaction, or it could be electrostatic interaction. I can tell you something we did recently. We mixed the epoxy resin with styrene, butadiene styrene. If you simply put this material in epoxy, there's no interaction. You know what my PhD student did? He did epoxidation of double bond of butadiene. Once you do a little bit of epoxidation, these epoxy resin love this epoxy group. So you have to do some chemistry on the surface of this filler. Then you can make a very strong interface. So I always advise my students, chemistry plays a paramount importance in making a strong interface. So you have to have some sort of, it's very simple chemistry, can make one day. So my suggestion is, you have to modify the filler surface so that epoxy can interact with the functional group of the filler surface.
I don't find any other question from the chat box, so I request the chairman to continue.
Okay, so if there is no other any question, so sir, let us thanks Professor S. Thomas for his excellent talk and a very informative lecture on polymer nanocomposite in different field of biomedical as other functional materials. Sir, we are very happy to see your talk, and thank you very much for this lecture. Thank you, sir.
Anil, for giving an opportunity to interact with you. I wish you all the best for the wonderful conference. And I welcome all of you to my campus after COVID.
Yes, sir. You have given very nice overview of your campus as well as different sites in Kerala.
Sure, sir. Definitely will come, and I hope you will come in our KIIT University and have a wonderful program. And by your blessing, we can go a different level of polymer nanomaterials.
Yes.
Nice to talk with you, sir. And your one blessings to all the young participants can go next level, sir. Thank you, sir.
We can have a very active cooperation between your institute and my institute.
Yeah.
We can have MOU, and your students can come, my students can visit you, and let us have lots of interactions. Thank you so much.
Okay, thank you, sir.
Thank you.
So let us move to the next talk of this session. So I think the next talk is by Dr. Prasanna Kumar Sahu. Dr. Professor is available?
Yes, sir. Yes.
Yeah. Okay. So welcome, Dr. Prasanna, for this second talk. So his topic is on this emerging two-dimensional lateral heterostructure for photoelectronic devices. So I am going to just give a brief introduction of Dr. Prasanna Kumar Sahu. Actually, he is currently assistant professor in Material Science Center, Indian Institute of Technology, Kharagpur. He is mostly related to the his work is very in the two-dimensional material for the heterogeneous, which both have a fundamental and wide range of technological application in future photoelectronics. and LED, photovoltaic, and quantum technology. His work also have a different nanomaterials that includes 2D material and heterostructural graphene, semiconductor devices, fabrication of physiochemical property assessment of these composites, and actually his educational background, he is a master degree from Sambalpur University, and he has PhD degree from Homi Baba Atomic Institute, Kalpakkam. So, and his research career includes he has a postdoc from the Institute of Physics, State University of Campion, Brazil, and during 2013 to 2015. And after that, he moved to the another postdoc. So in 2016 to 2018, he did his another postdoc from the Department of Physics, University of South Florida, USA. And during 18 to 19, he was a research associate at Cambridge Graphene Center, University of Cambridge, UK. And from 2019 onwards, he is in assistant professor in IIT Kharagpur. So he has, apart from this, he has a different many awards on his credits. He has got a University Gold Medal award for securing first position in Sambalpur University during his, I think, his BSc in 2007. And he has got a Best Paper Award and first position in Young Research category, International Conference in Nanoscience and Nanotechnology, Hyderabad, India. And he have a postdoctoral fellowship in Brazil and other, I have already told you. He has many research papers on his career, and he is currently involved in different subjects of teachings, and also guiding different PhD and master students. So with this short introduction, I am going to invite Dr. Prasanna Kumar Sahu to give his lecture. Dr. Prasanna Kumar Sahu, please.
Yeah, I will try to share my slides.
Yeah.
Just a minute. Thank you, Professor Anil and Professor Parasar and Professor Pradhan for inviting for this excellent conference to give a glimpse of our work, what I did so far on the area of emerging area for 2D materials. Basically, my focus on how we can design different kind of 2D material to make heterostructure and how we can harness very unique optoelectronics properties while arranging them in a particular order. So the big motivation is here. All you can hear me, right?
Yeah.
Okay. The big motivation is here, the day-to-day life for sorts of new materials. So you can see in this graph, in this plot, you can see the by 2030 is mostly the market will be dominated by transistor and neuromorphic computing kind of device because of the increasing demand of electronic component in our everyday life. With that, if we will use the conventional materials like silicon or conventional 3D materials, then we know there is a scaling issue. We cannot reduce to particular thickness limit. Otherwise, the device properties will vanish or the mobility decreases drastically. That you can see from here. If you below a threshold of thickness limit, the conventional semiconductor like silicon and gallium arsenide and other materials, their mobility drastically falls or reduces. Whereas there is a new class of material that recently emerging in the decade of in a few years, that WaC2 or tungsten sulfide, tungsten selenide, molybdenum sulfide, molybdenum, their mobility is quite comparable as compared to bulk conventional semiconductor. From that context, and the thickness you can see here is below 1 nanometer. That is a phenomenal. Means your device size can be thin enough at the same time you can achieve the required mobility while using this material as active component of any semiconductor devices. And another increasing passion is going on. That's we demand our electronic devices to be flexible. And with that flexible, we can see that there are many different application of flexible devices, that e-tattoos, wearable electronic sensor, smart watches, and smart glasses, and smart tablet like smartphones, and all these things we want flexible, to make our life more convenient and affordable, and easy to handle them. And also in some application also require transparency. And what we also need along with this part is high performance. If it's not high performance, like we don't want to charge our cell phone or mobile for 2 hours or 3 hours. That's why we want to have smart performance, and we at the same time ultra thin body and devices. On this ground, 2D material that I'm going to talk very soon, those can be a very good like competitive material to achieve all these objectives. And if you think in a broader sense, one of the broader sense is, whole world is full of Wi-Fi signal. Suppose whether we can harness this Wi-Fi signal to self-power our electronic devices for mobile and for our laptops. So in that sense, recently from MIT group, they could achieve using these 2D materials, they can able to harness this Wi-Fi band radiation, they can convert it to DC current, and this is how it is possible to recharge our electronic devices without using any charger or external sources. That will be phenomenal, but still we need a lot of to make it commercially viable. We have to completely understand the behavior of this material and the extrinsic parameter that affect its physical properties. To give a very good sense of what 2D material looks like, you can think about like the potatoes. That's kind of 3D material. If you break it, you cannot be gathered. Literally, you have to chop them out, to make slices. So they are covalently bonded between different planes. And if you think about onion, so we can peel off layer by layer, and that's the graphite. So this is called onion. This is what looks like a bulk 2D materials. Between different layers, there's a van der Waals interaction. There is no the weak bond, so that you can easily exfoliate this kind of materials. Whereas in kind of 3D materials, the bond between different atomic layers are covalently bonded. So it is very difficult to release them. Even if we can release them, but they can be very prone to oxidation because of the dangling bonds that damage the physical surface properties. So here is a clear resemblance from bulk semiconductor to 2D semiconductor. We can see that bulk have a lot of dangling bonds, and that is prone to oxidation and changing the physical properties. Whereas a 2D semiconductor surface is atomically flat, and that gives rise to, and is very stable, and this is give rise to very unique properties. And this family is quite big. We can get boron nitride, which is insulator and excellent dielectric material, and graphene as a semi-metal, and there are semiconductors like molybdenum diselenides and black phosphorus. So you can see from the periodic table, there is an enormous opportunity to combine different class of material to form different 2D materials. Mostly the transition metal dichalcogenide, that are what we are going to talk is mostly we take on molybdenum and tungsten, and we take this group 4 elements, selenium and telluride or sulfurs. If we check the 2D family, now we have plenty of rooms to class of in different class of materials like graphene and we have boron nitride, and there are fluorographene, all these graphene and 2D chalcogenides. Here we can get the semiconducting material, 2D material. There is other kind of semiconducting dichalcogenides, and also we can get metallic dichalcogenides, and those are also belong to the same layer structures. And in this talk, I will mostly focus on these 2D chalcogenides. With this, my plan of talk is how we can create, in going one step further, how we can control the materials to synthesize them or to fabricate them with a precise order and a precise manner in order to control the carrier in a specific way we want. So with that, we can see that by changing different kind of order and synthesis stage, we can control their phase, we can control their, manipulate their charge, we can control their carriers and spin, and then we can make into very unique devices out of it. With this, I will discuss about the 2D heterostructure, how we can create those kind of atomical thin materials. You can think about is the thickness is 0.6 nanometer. With that, we can control literally the lateral direction. We can change the material the way we want. So this is how we recently developed this method, chemical vaporization the method, where you can grow this kind of structure. And you can see this is a very simple method. Unless your technique is simple, it will not lead to a tremendous progress in industry. That's why you have to develop a very simple method. And in our method, we develop the simple water and hydrogen as a carrier gas, and selectively we can grow one material at a time and at a specific location. And we can sometimes say it's edge epitaxy. It grows specifically at the edges of one layer, not on the top, unlike 3D semiconductor. And also other process, by using a laser, we can also locally, in the 2D material, locally we can create heterostructure that I will touch upon. And in this class of matter, there is very interesting properties of exciton that can have, we can form trion, bi-exciton, more exciton, this kind of different exciton we can also form. That we will discuss a little bit. And also in the device part, I will show that whatever the 2D material we can synthesize, we can show that they can be used for room observing or realization of a room temperature light emitting diode, and also photovoltaic devices we can use. So there are many more. We have recently, there are many more opportunities to combine and to harness the interesting physics out of this material, because this is still a black box. There's a lot of interesting physics are emerging day to day, as magnetism, topology, unconventional superconductivity. All these phenomena can be realized, which is absent in their Ball counterpart. That means there are new discoveries still awaiting in this class of materials. In going to a little bit, just giving a brief introduction about this crystal structure of the materials and the properties. This transition metal dichalcogenides are nominated MX2, M is metal and molybdenum or tungsten, X can be selenium or sulfur. For you can see that unit cell is a trigonal prismatic structure, and there is a van der Waals gap between these two. And because of in a monolayer, this is the broken symmetry, this different new properties emerges. And it is a typical unit cell. From the top, if you see it, it looks like a hexagonal honeycomb lattice of graphene. And in a vertical stack, suppose you stack in a different layer, when I say it's a monolayer, that means it's a 3 atom thick, and one is metal layer, it's sandwiched between two chalcogenides layer, and one is called one monolayer, and this thickness is around 6 nanometer, 0.6 nanometer, means 6 Armstrong. And between two layers, there is a gap, van der Waals gap, and that's how it can easily remove. And one interesting point is, within a monolayer, the absorption coefficient is almost 20%. That's how it make a big difference as compared to the bulk semiconductor. And another very interesting properties of this material, if bulk material, if you see the band structure, this is a indirect semiconductor material, because the conduction band minimum and the valence band maximum lies at different K point in the band structure. Whereas if the moment you thin down to a single layer, so what we can see, this direct band gap tension can be observed at a K point. That means that indicates unlike conventional semiconductor, the quantum yield of a materials will depend upon the amount of your materials. But whereas in this class of materials, when the moment you are reducing or thinning down to the material, you are increasing the photoluminescence quantum yield. That you can see from our measurement here, that from MOSC2, you can see that in monolayer, these are super strong photoluminescence characteristics, very narrow band, as compared to bilayer and trilayer, these are drastically reduces. And giving a comparative picture with the other class of 2D material, in graphene, we can see that the direct material, the band structure are touched at a point. This is how is not a semiconductor. This is limiting the application in the semiconductor industry. Whereas boron nitride, the band gap is 2n is more, that's why it is become insulator. But this can be used as a very good dielectric material. And in TMD, the band structure is again is very unique, and the valency band is degenerated. That means then we have, along with your electron and spin as a degrees of freedom, we have another degrees of freedom that add into the system. So that's why making a new field emerging, that's called electronics. That's why making this 2D system is completely interesting. So from the exciton point of view, the new physics we already discussed. In conventional semiconductor, the exciton binding energy is very low. That's why it is very hard to observe at room temperature. But whereas in 2D materials, the binding energy, exciton binding energy is quite large. It's half an electron volt. That means this is quite stable even at a room temperature. And majority of the photoluminescence spectra of 2D materials are dominated by excitons emissions. And you can see that in bulk 3D, the excitons are delocalized because of the strong, weak interaction, Coulomb interaction. And this is how the exciton binding energy from band structure we can see about. But when you moment you thin down to monolayer, due to the strong screening and Coulomb interaction, the binding energy of these excitons are stronger. And these excitons, once it is formed, they are like a free quasi-particle. They can move through the surfaces. This is how in the future, and in adding to the another advantage that they have a strong binding energy, they can be stable for a couple of time, means they have long lifetime. So we can realize exciton-based devices only with this system. So in addition, so this exciton can be easily combined with, if you have a higher number of carrier, you can form trion, and even if you can form bi-exciton, pentanon, or exciton, this kind of structure even you can form. With because this bi-exciton we can form by applying magnetic field, or if you have low temperature, those kind of system we can observe. And why these are important? These are important from the point of view of quantum computation and quantum sensing, because these are they have a trivial, very specific states, quantum states that can be uniquely assessed, not interfere with the other system. And very recently, we can also form polarionic trions. In the trion, when in the presence of in some magnetic field or orbital optical modes, rotational orbital mode, we can form also trion polaritonic trions. So those kind of system also. There's a lot of new things are emerging in day by day. So the last 1 year, so there is new physics are emerging. Suppose you have a piece of 2D materials, and the TMD material, and stack another layer of material, you can see that the artificial structure is forming. That's called Moire patterns. And especially in the TMD, this Moire pattern can be a source of trapping of excitons. So they can be useful. They can be a source of quantum emitter at a particular location. So and there is a very opportunity. We can keep rotating with a particular rotation angle. So we can varying this pattern and varying the that means you can think about this enormous range of way we can handle this material. And as I told you, this exciton is very stable, and using this concept, what we can do, we can make a very atomical thin photonic devices. That means in many photonics, your material size thickness should be comparable with the thickness of the wavelength of light. Whereas, but how we can with 2D metal, how we can guide light? Then what we can do, we can shine laser and convert it to exciton. That exciton can diffuse, and you can collect it at the output. That means you can communicate using the exciton, not with the electrons. These are the new things are emerging. Now we'll go to the how we can manipulate this kind of materials precisely at the atomic level, not to just for the sake of paper or something. You can just exfoliate one and the other and stack it. But we have to find a method where we can form this kind of heterostructure, means combine different materials and they form heterostructure. Before that, what are heterostructure? Because I think there are different audience, maybe they will need it to know the fundamental of heterostructure. Heterostructure are if you sandwich between different materials, suppose you put different band gap, then you form a heterostructure. If you combine AB like many, then you can form a multi-junction heterostructure or quantum wells. Depend upon the size of the width of the barrier and the width of the potential well, we can form quantum well and dissipate energy levels. And if the barrier is thin enough, what happens? The energy states of different potential well can interact and can form mini bands. This is how the concept of superlattice. Using that concept, the 3D semiconductor superlattice people made using the pulse laser diodes, different band structure. They are very useful for multi-junction solar cell, where the electron can tunnel in one side, hole can move in other side. This is how they could able to achieve like 46% of solar cell efficiency. Otherwise, if you just use the raw material, your efficiency will be you cannot achieve that much efficiency. But another giving hand to the 2D semiconductor heterostructure, it is easy to make this kind of vertical stacking, and also it is that's in our method we can find a way that in situ without disturbing anything, we can also create fast time to get this kind of heterostructure in the lateral directions, the 2D lateral epitaxy. So why the heterostructure are useful or interesting? You can see there are different types of heterostructure. One is type 1, type 2, type 3, and it depends on the band position, and their carrier can be confined or that can be useful for laser or LED. And you have a type 2 where a band, if the carrier move in one side, other side, that can be used for solar cells or exciton-based devices. And also type 3 where we can make tunneling. Your band to band from one metal, band from other metals are positioned in such a way that carrier can easily tunnel. That can be find tunneling diodes. So so that's how you have plenty of opportunities. You have different materials and it depends upon your application. So you can find a right combination of your 2D material to enable impressive devices. And another major difference in 2D semiconductor and 3D semiconductor, in bulk 3D materials or PN junction diodes, you have extended depletion region, and the most of the carrier are due to the diffusion or drift based diffusion. But whereas in atomical thin, your material is already thin enough, so there is no extended depletion zone. So, but most of your carrier is happening due to the tunneling is due to the tunneling, and that's why since it is this carrier recombination mostly due to the tunneling based, so there is a ultra fast charge transfer can be take place in this kind of when you stack this kind of materials. That means your device we can make ultra fast devices. So you can see in this chart, beautiful chart from this paper, there are many different class of 2D material and different semiconductor. By combining different materials, you can observe, you can realize many different type of heterostructure. So you can see here. That means you have plenty of opportunity to play around to this field to combine. That means and also you know that this 2D family constitute of metal, semi-metal, semiconductor, insulator, superconductor, topological insulator. There are a lot of opportunities. That means by combining different class of materials. So, however, the current status in terms of in the domain of light emitting diode or solar cells, the efficiency of the devices made out of this kind of heterostructure is quite low. Because of there is a fundamental, there is an extrinsic factor which affect the physical properties of this material that need to be probed. That's why we used to get solar cell efficiency of less than 5%. Even for electroluminescence for LED application, the efficiency is also quite low. It's around less than 1%. That means there are ample of room for further improvement, and one can take challenges in this field. So going to the challenges, suppose you want to make a LED, you have to stack in many different materials. There will be contamination while stacking and position, right, exactly positioning the different materials to make a structure. So in that context, some people already started to grow this kind of structure in the large scale and assemble them afterwards to form large area heterostructure superlattice. And also, but most of the case what happen, we don't have control of positioning one metal over other. There will be contamination at the interface, and there will be rotation angles, and that's why limiting the efficiency of most devices. However, suppose vertical heterostructure is very easy, you can make it mechanical stacking. However, if you want to connect metal in one end to the other, it is not possible by mechanical exfoliation. That have to be done by growth only. There where our expertise lies, how we can control this lateral epitaxy. In this context, there are a couple of papers. Their first paper start from 2014. So here people use single step, they use molybdenum, tungsten, and tellurium. There are mix of power. That's why the field could not evolve properly. Means it is very reproducible, was a big issue, and the mechanism was not clear, and the interface was quite bad. And with that, further, there was a two-step process. You grow on one material, and then you grow another material and form the heterostructure. Then again, this is reliability large scale application is limited because the 2D metal is very sensitive when you grow for 2D steps. In this recent, there are also in the recent time also they're using these two-step, the multi-step process. People can make a heterostructure. However, we need a in situ strategy where we can control on different layer directly, not removing and growing again from the CVD system. This is where our expertise lies, where we can create those kind of unique structure lateral junctions in one-step growth without breaking any environment, CVD environment, in situ and in a very efficient manner. So we can see here, so we can grow molybdenum, tungsten, and we can control their thickness and control their wave. We can make superlattice is from sulfide. I will discuss more on that. This is also alloy-based 2D material. This all together we can control many ways. And so far, this is the most flexible and scalable approach to create those kind of heterostructure. And in future, whether we can integrate in 3D and 2D in 2 dimension in this structure. How we create this structure? We employ mostly the chemical vapor deposition method. What is CVD? Which is called CVD. CVD means a chemical reaction occurs. The standard chemical concept sometimes like thermodynamics, kinetic concept theories applies. And your vapor precursor react in gas or vapor phase. And the concept of vacuums and evaporation rate, all these concept comes in this part. And deposition, a solid product that formed during the interaction that will deposit on a surface, and then epitaxy and this growth occurs in the substrate. That means in the typical CVD system, you have a quartz reactor, or you can say quartz furnace. You have different temperature zone, and you can flow to different carrier gas. One is nitrogen with a small amount of water vapor, and another is argon gas with reducing gas as hydrogen. And you put all your precursor at one place, and you flow one carrier gas at a time. Then it will evaporate one metal, depend upon the carrier gas, one metal evaporate and deposit. And it evaporate because of the high temperature is more than their melting boiling point. So they will evaporate and then form a gas phase. On that gas phase, they can react and fall on the substrate, and they start nucleating. And this reaction in this most of the 2D metal mostly as a solid vapor reaction, most of the solid precursor, solid state vapor, and converted directly to the substrates. And you can see here the incoming precursor can come and attach on the edges. Why on the edges? Because this 2D metal, you remember, if you have high quality 2D materials, the top surface is there is no angling bonds, is van der Waals bond. So atom fall on the top, even if they will try to roll down to the bottom edges, because of there is no step edge to grow. That's why they keep growing on two-dimensional plane. That is one advantage. And these CB systems are very important because these are large variety of film we can make, and this is also scalable and low cost, and the stoichiometry control is rather easy that compared to other like expensive technique like MB or MOCVD. We did let go a little bit to probe the underlying mechanism. So what you can in the long story short, I can say that if you put two material, molybdenum sulfide and tungsten sulfide, suppose you grow one material carrier gas, when carrier gas is hydrogen, water vapor, nitrogen with water vapor, you grow molybdenum sulfides. The moment you switch to the moment, that means when in presence of water vapor, it promotes the growth of molybdenum. The moment you switch to the argon and hydrogen, what happens? The molybdenum precursors suddenly deplete, and the tungsten precursors start growing, evaporating. That's why you can keep growing the tungsten at the edges of molybdenum. And if you, the moment you keep switching on and off, then you can create this kind of again molybdenum. You get heterostructure. And that you can see from a typical image, ACM image from a very nice single crystals of molybdenum selenide, tungsten selenide, molybdenum selenide, tungsten selenide from that. And here we go, I'm not going more deeper in this field, is more specialized because it is a more specialized interest. So what we can see in the first stage, what happens, the molybdenum bulk materials, water interact them in the form of volatile species, it form molybdenum dioxides and the tungsten oxide, but molybdenum tungsten oxide is still stable in presence of water vapor at that temperature. That don't contribute to the growth. But molybdenum oxides are that whatever forming, they are more volatiles. What happens, that contribute to the growth and they form the crystal. So that's why it is forming a very like tuning. One, it is locking one and is allowing the other to grow. And the moment you change to the reduced gas, the hydrogen gas, what happens, the growth of tungsten is promoted. Molybdenum is reduced to molybdenum, metallic molybdenum, and metallic molybdenum, it is not easy to evaporate at that temperature. That's this part is stopped and it is contribute to the growth. Tungsten contribute to the growth. And this process, molybdenum, that's why I told, these things are again, tungsten also reduces in the presence of water. At the same time, they reduces as well as they are contributed to the growth. And if you keep switching the stage between stage 1 and 2, and you can create this kind of lateral heterostructure, very unique and a very single crystal. Yield is very high. And there is another important part is, suppose we grow, we can control only single layer of a lateral epitaxy. And whether can we also grow bilayer of a lateral epitaxy? How we can control the layer number at the same time to maintaining the heterostructure part. And we all know that civil process is quite complicated. There is a lot of parameters like kinetics, thermodynamics, and thermodynamics play in very important role. So it is very difficult because you need a long time to optimize some parameter. Suppose you have to fix one parameter and you play other, and you cannot at the same time vary many things and try to optimize. And in order to control, that's what in our next approach in the second follow-up paper, what we try to do in order to the temperature of the substrate to manage, keeping all other parameters same, just keeping the temperature of the substrate, and we could able to control the bilayer and monolayer or in between. This is how we can come. Then the K or kinetic coefficient of bilayer and monolayer from this equation you can find. So we could able to control the number of a layer, maintaining the edge epitaxy. So why the monolayer bilayer are important? You can see that the edges are, there is a barriers, activation barrier at a high temperature. The barrier is a little bit lower, and also the initial nucleation can be a double layer, so that can keep continuing. A tri-layer, the barrier will be higher. The more bilayer, this fast barrier is lower. That's the material can easily promote on the bilayer growth. This is how keep growing. So how we will characterize this kind of materials? So first thing is, one good important thing is we can easily identify this material with its conventional optical microscope. So we can see here, suppose you have a different silicon substrate, SiO2 layer, and your one 2D piece of 2D materials, they have different refractive index. and in respect to air and other substrates. And that due to the in the monolayer, the absorption threshold is more than 10%. You can easily identify a single layer. You can see that. If you have bilayer, the contrast is different. You have a tri-layer, your contrast is different. This is how we can easily identify. We don't need to go to a conventional TM or something to characterize whether it is how many layers. So we can easily judge it by a simple microscope. So from here, you can large scale, you can view, you can see a monolayer, how it looks like similar triangle with a bilayer, how it will look like at the same magnification. This scale bar is around 10 micron. And Raman is a very powerful technique to characterize this kind of 2D materials. So you give a fingerprint of your chemical compositions. So you can see that when you have tungstens and molybdenum, so they have tungstens. This is molybdenum selenide peak A1G mode, which appear around 240 centimeter inverse. And this is for tungstens. They are unique. Their position is unique. And basically this for those people not aware about that, the A1G mode is that the out of plane vibration. E2G mode is in plane vibration. And this is give a characteristics of a particular material. And we are not bothered about the character in the Raman. What we use this technique to see how this composition varies within the domain. Suppose you take same monolayer and you take a raster scan across the surface by point. So what then you get a collective large number of spectra, and you choose a window of this range, and you see how the molybdenum peak 440 centimeter inverse peak distributed. You can see it only distributed in the inside campus. That is the molybdenum selenide, diselenide. And if you choose the other peak, this peak A1J at 250, 49 to 50, then you see the tungsten, how tungsten is distributed. And you can see that the clarity of the image that indicates this because the crystalline quality of your materials. They are very homogeneous and very high quality. And if you take a position map, you can combine these two and you can see the same heterostructure like that. Again, if you don't trust these, and you can take a position map, you don't process anything, just check what are the maximum intensities, what are the position map, then we can also get how the two positions are distinctly distributed from 230 to this range. This is a unique. This is how we can identify that the heterostructure, there is no diffusion of material from different material. And we can identify them as from your PL spectra. In monolayer, you know already, I told you this is very strong photoluminescence, bilayer, trilayer. That way also you can identify. For tungsten and molybdenum, their position is different. That I'm going to talk in the next slides. So in employing the same method, we can make more complicated heterostructure like molybdenum, tungsten, these 4 junctions. You can see that we can make single crystal, very uniform size of 300 micron around. We can even make bigger, but you can see that this is also even big a game changer. It's like a big crystal. Lot of device can be realized in this kind of size of crystal. So how we characterize, even we can make a very systematic 5 junction, even just 2 minutes of growth in between. So how we'll characterize this kind of structure? So to understand more better, if you take a Raman spectra from different 4 domains, so you see how molybdenum tungstens are situated and lies in these things. And if you take PL from different junctions, you can see this how their position changes. This is how you know that. And you take Raman spectra, and if you choose a map, and you can clearly map the domains. In the Raman, you can see that how the domains are distributed. Very nicely they're distributed in the small scale. And for PL also, you can check how the domains are distributed. And if you combine, you can see the heterostructure. And for application for many devices, interface quality is important. That will give you information about how carrier will transform from one side to the other. So during the growth, you can see that if you take a contour map, if you take a line map from the middle to towards the edge, and take a contour plot, you can see that the first interface is the PL spectra is shifting continuously, whereas in the second interface, when you're moving from tungsten to molybdenum, the interface is quite sharp. That indicate that from the PL contour plot itself, there is anomalies. That in the subsequent slide show you why it is so. So we know to understand more better way, we use this material for we further study the HRTM, the high angular dark images like TM images, where you can study is a STM images, and in the STM, TM based STM images, the jet contrast is huge for tungsten as compared to molybdenum. That's how you can clearly see the differences in their contrast. And is good. This material is, even if it is 0.6 nanometer thick, it can easily exfoliated. Like if you put a KOS solution, you can peel this with the help of a polymer, the entire film, and you can put in the holes, polycarbon grids, and that you can study how the heterostructures domains are there. And if you took high magnification image, you can see that is a tungsten part, and this is the black side is molybdenum part because of the intensity contrast. The scattering contrast is different for tungsten side as compared to the selenium sides. But two selenium and molybdenum are say contrast, that's why the intensity height is similar. From that you can identify the type of material. And when you have a diffuse interface, then your some material will interface, and that you can identify from your line map from your PL. If you have a sharp interface, you can directly see there is a distinct junction from PL emission. If you have a diffuse interface, then you have similar this kind of structure, the gradually increasing the PL spectra. That indicates Raman and the PL itself can be a fast under tool to identify your interface nature. You don't need to go to this high-end like STM technique. This is very expensive technique. That's not readily available for everyone. In the similar manner, we can also grow the sulfide-based heterostructures. Sulfide-based heterostructures, and you can sulfide this. There before we saw the triangular shape. Now this is truncated tetrahedral or a truncated triangular shape. And because of different metallic or chalcogenide edges, because of some growth rate is different in different domains, this is how, depending upon the type of metal or precursor, you end up with a different shape and size. And this is also important. If a different shape and size have different chemical potential, they can be used for particular applications. And again, I don't need to go through again all this. This is the same thing we can characterize the Raman and PL. You can see how distinctly the domain and distributed. And in case of WS2, most we can see that all interfaces are of high quality and the speciality well defined. We can interface. We can see that. Not only that, suppose your fundamental material is only 4 molybdenum and tungsten selenide sulfides. So you are not, we are not limited by only 4. What is the advantage that you can combine the sulfur and selenide also, that also we can realize many different composition, and we can vary systematically their composition. And if you calculate the internal energy of mixing of different material chalcogenides, you see that sulfide and selenides, their internal energy mixing is negative. That indicates they can be easily mixable. We can form easily the alloy structure. So you can see from this effective band structure for sulfide and alloy-based structure, you can easily tune their band positions and still retaining the direct band gap nature of this material. This is phenomenal. Using that concept, so we use a different selenium and sulfur precursor to tune the composition of the structure of alloy systems, and using the simply by the Vegar's law. From that, you put the band gap energy of the molybdenum sulfide or selenide, then you can find the composition if you have alloy. That again, you can see that we have a line map. We see even if it is forming alloys, then even if they are not mixing, they are spatially distinct. And from the HRTM, from the head of STM, we can see that spatial position of the tungsten and selenium's atomic sites. They are distributed unevenly. From the position, we can also identify what are the composition. And in summary of this shape and the structure, as I told before, a few keywords. So in general, this hexagonal cement should be hexagonal shape, but depending on the molybdenum to sulfur ratio, if the molybdenum ratio is higher, they need to promote the growth of molybdenum and to complete the edges are molybdenum. The shape will be like that. So when you have a very stoichiometric ratio, you can end up with a particular hexagonal symmetry. And if we off in the sulfur ratio or is higher, then we can end up the edges are terminated to the sulfur mostly. This is how we grow the triangular shapes are obtained. And not only that, one step critical that whether we can make even like it's a CVD system. You have to remember CVD is very not like MB where you have a ultra high vacuum of order of 10 to -8 to -10. Here it is all atmosphere. Within that conditions, we can make this kind of atomic lines of 100 nanometer. But in this case, we cannot easily identify it with the conventional microscope. We need an atomic force microscope using there to characterize this kind of interface. And with the snob-based technique, we put a laser at the apex of the tip of the FM tip. It's called popularly known as snob tip. There we can get this is get a PL image, localized photoluminescence from each position. This is not atomic topography. This is photoluminescence topography, where we can see the step edges, how they are varying in the lattice directions. So we can see that if there is a defect, because this metal is very prone to degradation. I am not going deeper in this topic. So if there are defects, we can see that photoluminescence quenches at this localized defect sites. That we can identify in much deeper with this kind of snob technique. And another important, the bilayer these days are becoming a very important class of material because of there are many interesting physics. So the bilayer, even they have a different polytypes. You can arrange one layer over the other in a different order. This is depend upon that their properties slightly varies. And most of the bilayer stable configuration to AC phase, where and also in bilayer why it is important. In addition to direct transition A and B, you have also the indirect transition that also can contribute. So you have in the PL, you can observe, we can get this kind of bilayer unique structure. I'm not going deeper. The similar way with the CVD system in our adapting method. You have a A exciton and indirect exciton, and in molybdenum you can easily see the B exciton and A exciton, and we don't see the indirect. So in combining, so you have a different way to manipulate this kind of material while tracking them in a different order. Similar, you can, even if it's a bilayer, you can see the photoluminescence, there are drastically changes from domain to domain, and that means they are spatially distinct. And also you can see the TM image, head of STM image, where you can see distinctly different domains. That means this method have a very potential, we have a very strong potential to realize different kind of material. And I'm not going here. Initially, I told you we can order the stackings where you can harness more excitons, and we can, if you have a different rotation, so there's also have a different potential that we can see that of the sample we are trying to growing those kind of with different rotational angles. So we can see that 60° and here is a 0 degree. With that, we can see that we have, if you have a 60° and 0° rotation, and your PL spectra is completely modified as compared to your normal PLs. And if you have monolayer, then you don't see observe those kind of peaks. And those have a different application. There are a lot of papers ongoing on those directions.
Excuse me, Dr. Sahu, can you, because your time almost is going to finish, so can you finish in 2, 3, or 5 minutes?
Yeah, in 5 minutes. Okay. Okay. So this is another method. I am going faster. Then this is the laser-based modification in the surface. We can tune with a reactive gas. You can modify the surface easily in this kind of structure. I'm not going to. Okay. So one interesting that in the Raman, what we can do. Okay, the video is not working. Where you can locally see that the molybdenum selenide is converting to molybdenum sulfide. So we can, if you take particular Raman modes, and you can see that by laser you can modify one material to other materials, and from that you can get the time constant of reaction rate, all the information you can get. Even you can modify tungsten selenide to tungsten sulfide, which is quite interesting. You can see the PL spectra here, and also PL spectra with the 2 minutes, several minutes. We can modify the material into another materials. Okay, in TM confirm. Now I'm going to the more device part, interesting part of the talk, but due to the time limit, I will skip some of the discussion. One important thing I would like to cover in the bulk 3D materials, you need a more higher gate bias to mobile the material because their distribution is quite large, their functions. Where in 2D matter they are already confined, so with easily low gate bias, we can easily control this kind of carriers. So, and it is very device point of view, there are a lot of challenges because it's very atomical thin materials, how you deposit metals, how you create your, how the carrier will inject, there are a lot of things. And there are a lot of device concept are conceptualized using this kind of 2D material like lateral heterostructure, TEFET using lateral heterostructure. But there are a lot of conceptualized, mostly depend on tunneling. The device concept there, and based on that, there are a lot of application in photo detection, in photoluminescence, photovoltaic LEDs application are coming on this field. And in our materials, using that same heterostructures, so while PN junction, we make particular devices where we can assess that we can from the transport measurement, we find that WSE2 is a P type and MOSE2 is N type. That means we are growing directly PN junction is a one step simpler or closer to the reality. In conventional material, you have to dope and form a PN junction special. But here you can directly grow PN junction. That's a very challenging thing. And how you know is a PN junction, and you know when you shine light, the carrier can effectively generate it, and from the depletion zone can travel to different electron, and your current can increase. This is how you can show that you can say as a photodiodes, and you can get and I on off to ratio is 10 to the 5. That means it's a very promising material, and as compared to the most of the reported result based on mechanical exfoliated samples. Also in bilayer, we have like same thing. We can observe also the photovoltaic effect at zero gate bias. You can set the short circuit current already due to the inbuilt potential. That means this material can have also can be used as a photovoltaic materials. So in terms of electroluminescence device, there are many many mechanism. So we can have PN junction, so where your current electron and hole can combine at the junction, give a light when you apply voltage. Or we have a interlayer. So we have interlayer exciton. So we have vertical junction, the carrier can recombine. There are a couple of papers are ongoing, like from in the worldwide, people are trying to study in this kind of structure, the electroluminescence properties, but the quantum yield of this kind of device is low because of several parameters, as I discussed in the beginning, depending on the type of growth method and the contaminations. And employing the same concept, we observed that using the PN junction, we could able to get a light emitting diode at room temperature. And a diode, as I told beginning, in principle, if you have PN junctions, the light should come from here at the in the recombination because of the from the conduction minimum of molybdenum to valence maximum of the tungsten. However, we observe also strong emission from this side as well. That means there are competing process, and in other hand, it is also good. You can get emission from different domain. That's how you can get into more realized white color. That's the need for requirement for LED for practical application. And the beginning, as I said, the current status is very low in this material still, but because of several factors, that's why a lot of the rooms are there to improve. And future technologies demand that in a single device, we can integrate different kind of device concept like memory, computing, sensing, communication in these 2D devices by 3D integration. That's the grand challenge or the grand demand of these materials to realize. In summary, there I saw that we can directly grow this kind of lateral heterostructure in a very, very conventional, very simple, cost-effective method. We can control precisely atomical interfaces. We can tune their composition, relative orientation, and interfacial quality. And also we can also show that we can use this metal low power optoelectronics. I acknowledge my previous groups work with at the University of South Florida, and also device for Luis Palica, magnetic lab Maglab in Tallahassee, and also University of Cambridge, and also I'm former supervisor. That part work I didn't show. And I just from recently I started my own group with the quantum metal devices as a laboratory with 2 PhD students and 2 MTech students. Just we are beginning our life. And thank you very much. And if you have any question, I am open to answer it. Yeah, I'm done.
Thank you, Dr. Sahu, for giving a very informative and fundamental lecture of 2D material and this actually this heterogeneous layered structure for many functional devices, and giving the actually characterization overview of this CBD material for the production. So here my one question for the application point of view. Can a substrate where you are growing this heterogeneous structure can be a any kind of shape, curvature, or it's require always a flat shape to get this heterogeneous structure as a uniform structure? Or a curvature shape of your substrate can also you can deposit the heterogeneous.
Also matters because the surface is play a prominent role. Most of the SI was stable at the temperature of our growth and depend on the reaction of your substrate. If your substrate is reactive with your incoming vapor, then it is very difficult to be nucleated.
Yeah.
There is also surface is important, especially for 2D materials. Not all material can grow in every substrate. Like graphene is more good to grow on copper, not on other substrates.
Yeah.
And 2D material is easy to grow on silicon dioxide, sapphire, but it's not that easy to grow on other substrate. Maybe it will be reactive with the substrate materials itself. So it also depend on the surface.
Means the question is the surface topography means it should be a flat or it should be a curvature, or you can also grow
it should be flat. It should flat.
So if suppose in any practical application a curvature surface where you want to grow this kind of structure, is it possible or?
No, that depend upon what kind of curvature substrate. Even if it's flat surface, if we can make it a curve, it may be possible. But if you are thinking of polymer surface, it's quite difficult. But what we can do, this material are easy to transfer. You can easily, suppose it grow on silicon dioxide, it's a large flake like 1 centimeter area. Even 4-inch area you can easily exfoliate without breaking the film. That's a methods to completely exfoliate whole layer, whatever you grow on a 4-inch wafer, then you can transport your substrate of interest. So that's
okay. Thank you. And there are some
questions in the chat box. So maybe I can read with your permission.
Yeah.
So there is one question from Diksha Mishra, and the question is: what are the conditions for formation of tryons? How to increase the quantum yield of even single layer of these WS2 or MOS2 because it is very less as compared to other fluorophores?
okay. So one thing, different materials. So the control the crystal structure is depend upon the stoichiometric ratio, as I mentioned in my talk. So we have to control the molybdenum metal to chalcogenides ratio. We have to maintain. If there you can maintain properly and you have appropriate temperature range, if you can form a stoichiometric ratio of your material, then your PL quality crystal structure wise it will be better. If the crystal structure is uniform and you have a less defect, then your PL yield will be also better. Quantum yield, and we cannot compare the fluorophore because these different materials have different applications. So depend upon your application, this material, and there are some people they can treat the surface with different chemicals, with like TFSI. So when you treat some chemical, then you can improve the photoluminescence. Again, your cost will increase because this chemical is very expensive and it's not environmental friendly. But that's what it depends. What kind of application?
So there is one more question from Jaisi Bharadwaj. Which substrate is used for the growth?
Yeah, it's a silicon with is some layer of 285 nanometer SiO2 silicon dioxide on the top.
Okay, so there are a lot of appreciation for the talk. I'll just read one of these. Very useful, fruitful presentation by Dr. Sahu, and starting from basic and ending with application. Really a big thank to Dr. Sahu. So there are, I don't find any more questions. So it's over to the chairman.
Okay, thank you. Thank you very much for giving the opportunity to speak it.
Thank you, Dr. Sahu. Very nice presentation. And I also thanks Dr. Anil Chobe to sharing the session very nicely and managing the time. So I request now R.L. Sharma, Chairman and Managing Director of SPL Pune Limited, to chair the next session of the chair.
Thank you, Parasar.
So he's the managing chairman and director. Chairman S. Rajan Sharma. So you have to share and chair this session now. And Patrick is already available. So thank you. And basically, Rajan Sharma is one of the pioneer in the, I can say, in energy storage in the whole world. Is a 10th position in the world, and many member of the government of India, even the policy making of the government of India, prime minister levels, and making a new revolution in the energy storage in the world level and in India. So thank you very much, Dr. Rajan Sharma, to chairing the session. Let's start this session.
Thank you, sir. Thank you, Dr. Paras, sir. And I'm really very happy to be part of this AFM 2020, and I have a long association with KIIT. So, and I'm really thankful. Actually, it gives me immense pleasure, in fact, to introduce one of my friend, Dr. Patrick. He'll be taking a session on thermal energy storage. And basically, to introduce about Dr. Patrick is adjunct associate professor in Griffiths University, Brisbane. And one thing I would really like to emphasize, Dr. Patrick is from Brisbane, Australia, but he has a very what you call it, has a big support for India for Atmanirbhar Bharat, because he is a chairman and a technical consultant for Bharat Energy Storage, who is world's first thermal energy battery manufacturing plant coming up in India. And we thank Dr. Patrick for being a good support for that. And I would like to convey that Dr. Patrick has a huge industrial experience. Massive, actually. It dates back to 1964. I think most of us were not even born, or would have been 1 or 2 years. So he has that kind of industrial experience, and too many associations supporting to what you call it as a research institutes and companies. So Dr. Patrick is a BTech, MTech, and a PhD from Griffiths University, Brisbane. His PhD is on advanced collision avoidance system for coal and what you call it as mine haul trucks. So it is, we find it, we are very happy to welcome him. Actually, he has also been conferred with some awards like Occupational Safety and Health Award, ACARP Award, ABC TV Inventor Award, and last year I remember it was Kanthal Global Award for innovation on heating technology. Apart from these awards and work in energy, he has to his credit some publications and more than 26 referred conference material. And he has been associated with CSIRO Australia and have done a project over 12 million USDs. So I think the number of projects were more than 12, and each project might be of that kind of thing. So I welcome Dr. Patrick. Dr. Patrick, the stage is yours. Thank you.
Thank you, Dr. Sharma, and greetings everybody from Australia. Can you hear me?
Yeah, we can hear you.
Yeah, that's good. I'm on board. So just bear with me. This is the first time I've been on a web presentation. So any mistakes that's made, please forgive me. But thank you very much for the wrap, Dr. Sharma. one of the things about having so much experience is I've lived a very long time. So, so this is where all that experience comes in. The talk today, I'm just going to share my screen now. Can you all see the screen?
Not yet, not yet.
Have you got it? Can you see the screen?
No, you have to click on the options, no? Share a screen, and there will be some options.
Oh, okay.
Yeah, though whatever slide is there, you have to select that, and then click share. Yeah.
Okay. Now, shall we try again? All participants.
I hope your PPT is open on the desktop.
Yes, it is.
So you can locate your PPT. Just click on that and press the share button, which is on the right side of the screen on that desktop part.
Okay, has this come up yet?
Yeah, so on your screen,
great.
You can see it. Good. Okay.
No, it has again vanished.
Okay. Since I've been promoted within Griffith University to professor, adjunct professor, so I must be doing something right. Just a background to this project. This started way back in.
Dr. Patrick, we are not able to see the screen. You can just click the button share, and once you click that, the desktop screen will appear on your screen. Just select the PPT what you have kept open, which we will. Yeah, right,
Okay,
correct.
I can see it now. Okay.
Yeah,
apologies.
and now you can proceed normally slideshow, which you normally do from beginning. Correct.
Okay, thank you.
Correct. Yeah, great.
Now, all participants, you can see the screen.
Yeah, I can see, but you need to press the beginning slideshow. Click that. Yeah, great. Thank you.
Okay, I'll just put this down. Sorry about that. Okay, where this started was about late 1960s. We were working on energy storage, mass scale energy storage for domestic and industrial heating using concrete and basically heating with electric elements. During that period, Philips Holland, which I was working for, a subsidiary of theirs in Dublin, in Ireland, were looking at Stirling engines and had been since 1937. The difference between a Stirling engine and a standard engine is that a Stirling engine is a closed cycle engine and theoretically operates under the Carnot cycle, which I'll come to later, and has a very, very high efficiency. What interested me at that stage was the fact that using the second law of thermodynamics, if we could store the energy over a very long period of time, then we could extract it with very, very good insulation. We could extract the energy over 24 hours. In those conditions, we were simulating what happens with an actual power station, be it coal burning, be it oil burning, thermal, of course, thermal or gas. In '73, we developed a storage heater using a Philips Stirling engine, which used lithium fluoride. Lithium fluoride has about 6 times the energy density, similar to lithium ion, 6 times the energy density of lead acid battery. And it melts at 870 degrees C, and we drove the Stirling engine from it. The basic problem with lithium fluoride at the time was it was shockingly expensive. So for going from mass energy storage at that point, it just didn't work for us commercially. So fast forward to the late 90s, I went to work with, I left Philips and I went to work for CSIRO in Australia, the lead research organization. And at that stage, they were looking for a device which would actually drive vehicles using stored energy for underground mine disasters. And I put a proposition at that stage to the coal ACARP, the Australian Coal Research Programme, to look at a vehicle that would actually store thermal energy, highly insulated thermal energy, and allow a vehicle using either closed cycle gas turbine or Stirling engines to go underground safely. And from there, then I looked at the energy storage and retrieval situation, where instead of looking at batteries as being a partial load for 4 or 8 hours, we looked at it to replace coal burning power stations on a 24-hour cycle. We could then take electrical energy from any source. We could turn it into thermal energy, then extract that energy as and when we required it. The obvious things that you need to do this is you have to be able to charge and discharge simultaneously. And at that stage, this looked to be a problem, which we eventually overcame. I'll just carry on. Okay, how did we manage to do this? As I said, with the Philips storage heater, we were looking at using lithium fluoride at a melting point of 870 degrees C. With the Carnot cycle, which is the theoretical cycle that Stirling engines operate under, the higher the temperature versus the higher the hot temperature, the hot side, versus the lower the temperature on the cold side, you get a very high Carnot efficiency. To the point where if you have your hot side, if you're generating on your hot side of your cycle at 1,500 degrees or 2,500 degrees centigrade, and your cold side at ambient, say 25 degrees centigrade, you have a theoretical efficiency of 94%. Just to put that in context, a standard internal combustion engine operates at about 21, 22% efficiency. So you're looking at nearly 5 times the efficiency. Now, when I had a look at the second generation of these, I decided to go away from lithium fluoride, which was still frightfully expensive, and look at other materials. And we looked at a number of eutectics and a number of pure materials. And the material that stood out after our investigation was silicon, semi-pure silicon, 99% pure silicon. It melts at 14 degrees C. It's very stable. And if you can extract the heat from it at that temperature into the head of your Stirling engine, you have a theoretical efficiency of Carnot efficiency of 78%. So what we needed then was we needed something to put this into. We would electrically heat this element using heating elements across the top. We bring the temperature up in here to about 1450 degrees C to make sure we've got full melt fraction here. We then need a containment vessel. And that containment vessel, we, after a bit of investigation, decided that graphite, sintered graphite, was the ideal material. Sintered graphite is very high thermal conductivity, up to 350 watts per square meter per degree C rise. And also in an inert atmosphere, it can be used over and over again. It has a melt temperature of 3,500 or 3,600 degrees C, so it was not going to 1,414 degrees C here was not going to shorten its life by any means. So what we did then was we made a bathtub from the from the graphite. We filled it with silicon. We melt the silicon, and we then use the molten silicon. The temperature migrates through the conductivity of the graphite into the head of the Stirling engine and produces motor power, standard rotary alternator. The heating elements we used initially were silicon carbide elements. We then moved to graphite. We then moved to graphite elements, and we're now looking at using silicon metalloid elements with a temperature of 1800 degrees C. a number of advantages of doing what looking at energy storage from this angle is because you're melting and reconstituting silicon, you can do this 1,000,000 times. Lithium ion has under ideal conditions, has a 1 to 2,000 cycle operation before it goes below 80% capability. With silicon, you can do this 1,000,000 times without any problem whatsoever. You get no loss of performance. Stirling engines, because they are closed cycle devices, can be operated for 40 years because there's nothing to cause a problem. And once they're kept properly lubricated and maintained, probably every 2 years, although there is some out there which are operated, which need maintenance every 10 years, this becomes really a set and forget device. What are the advantages? The materials are plentiful. The energy density of using silicon sits at about 20 times the energy density of a lead acid battery. What this means is that if you're going to use it for mobile situations, it's mass by distance. The greater your mass, the shorter your distance. This is one of the limiting factors with electric vehicles and lithium-ion batteries. Because of the high energy density, you've got a very small footprint. At the moment, the price is comparable to a lithium-ion battery. Just a comment on lithium-ion batteries. I've been driving a lithium-ion battery-powered car for the last 8 years. Wonderful device. I've been using lithium-ion battery storage for domestic purposes. Again, work wonderfully well. One of the things I didn't realize, and my good friend Dr. Sharma pointed out to me last year, was the manufacturing of lithium-ion requires about 1 megawatt hour or 1,000 kilowatt hours for each kilowatt hour of battery. So in essence, if you're using fossil fuel to produce a battery within its lifetime, even if it's been recharged using renewable energy, it will never make back the amount of energy that went into producing it. So essentially, it's from a renewable energy point of view, it's quite suspect. Also, when it comes to the end of its useful life, really you have a situation where maybe 55% of the battery can be recycled, and the rest has to be thrown away. As against what we're doing, where all of the graphite and all of the silicon can be completely recycled, and the insulation, again, can be recycled to 95%. The casings on the heat cells are made of steel, so again, can be fully recycled. The elements, again can be, again, 95% recycled. So you're talking about an almost what's euphemistically called a circular economy device. So essentially, you've got virtually no waste from the device. The other thing we were looking at is that the availability of silicon, and with my good friends in India, Prakash, who's on the board of Bharat Energy, was stressing to me from his contacts in the government that this must be indigenous to India. And I was talking to one of the representatives of the Indian government, and he was asking me where would we get the silicon. And I pointed out the window at the nearest mountain and told him that that consisted of 27% silicon. So all of the raw materials for this can be produced in India. And India also has a very, very good manufacturing factory for graphite, Graphite India, wonderful organization. And they have made the first graphite blocks that we've used in our demonstrating cells. The life of the battery, we've taken it as a nominal 25 years. The only reason for that was when we were doing levelized cost of energy, it was a very handy number to compare with fossil fuel. Fossil fuel is taken from 25 to 40 years. When we took an LCOE using photovoltaics at a cost of about $1 a watt, the LCOE was about 1.5 cents Australia. What's that? That's about 3 rupiah. There's no material degradation, and the maintenance on this device is very, very low. Okay, a bit of history. I've just put this in because most of the people involved in battery manufacture are chemists. And chemists, God bless them, probably do less than a month of thermodynamics. So just to refresh your memory on why this works or where the history of this comes from, the Reverend Stirling in Scotland in 1816 developed the Stirling engine. It was an atmospheric Stirling engine, and he built in 1922 or 1822. He built a 10 horsepower version of the engine using cast iron on the hot side. It followed an idealized graph, your pressure volume graph, and it was one of the closest approximation to what we now call the Carnot cycle. Remember, in 1816, we didn't know what the ultimate expansion and contraction of gases were relative to temperature. The second guy we talk about is Sadie Carnot. Sadie Carnot was an engineer in the Napoleonic Army, and he came out of the Sorbonne, and he built a theoretical model of the Stirling engine. And we talk about the Carnot cycle now, and we're still relating all our theoretical modeling to the work done by Sadie Carnot in 1824. He died at the age of 36, which is unfortunate. Very, very bright guy. How does a Stirling engine operate? Well, a Stirling engine operates on the hot side versus the cold side. The hot side here, as you apply heat, the gas expands. As the gas expands, it goes through a regenerator. What the regenerator does is it scrubs off some of the heat from the gas as it goes through to the power piston. When it hits the head of the power piston, it pushes the piston down because of the pressure increase. As it pushes the piston down, the devices here, the radiation here, cools the gas. The now cold gas is pushed back through the regenerator, preheated before it goes back through the cycle again. And this would be considered what's known as an alpha engine. And once you apply heat, this engine will continue to operate. The RPM of this engine normally sits around 750 to 1000 RPM. This applies very little stress on the bearings and on the rotary parts of the engine. So essentially you have an engine that has a very, very long life. This is your Carnot cycle efficiency, TH minus TC over TH in degrees K. The equation speaks for itself. In standard combustion driven Stirling engines, they talk about having an efficiency of about between 32 and maybe 40% efficiency. And the reason the efficiency is so low, because you're using combustion during the null part of the cycle, where it's going into the cool part of the cycle, your combustion is still in operation. So effectively, you're losing between 35 and 50% of your energy. It's just being thrown out the exhaust. Or you can use it for preheating the combustion air coming back in, which increases the efficiency. With what we're doing, we don't have this problem. The energy that's in the head, in the energy that's going into the head here, as the cycle is going into its cold side, this is used as a preheater for the head. So essentially, there's no loss of energy through combustion. So when you do the calculation based on that, you find that you're now operating close to 60-65% efficiency. Our measured efficiency has been between 55 and 58% efficiency. This will increase as we get more efficient cycle in the engine. This means reducing the inherent frictional losses in the engine. Emmanuel Clausius, he essentially put words to the first and second law of thermodynamics, which we use. Our first law of thermodynamics is where we take energy, electrical energy from PV, wind, or hydro, or anywhere else we can get it. We turn it into heat, and then we convert that heat back into electrical energy from using mechanical means. And the second law of thermodynamics is where we, that's where it's, the first law of thermodynamics is that we generate the heat. And heat once generated, or energy once generated, can be neither created nor destroyed. Second law of thermodynamics is we just convert it back into electrical energy. Okay, an example of electrically heated latent heat cell. If we take a ton of silicon, as I said, this silicon that we use is called silicon metalloid, which is used in steel and aluminium, and it's used to give it its malleability. If you try to bend steel, what happens is it cracks. If you try to bend aluminium, it cracks. By adding silicon to it, it gives it its malleability, allows you to bend it and to shape it. If we take that and we heat it to from 25 degrees to 1,410 degrees, we get to its melt point. At that point, it starts to melt. We then pump in, to get to that point, we pump in 271 kilowatt hours of energy. Once we get to that point, from 1410 to 1414 degrees C, we have to pump in another 499 kilowatt hours or 500 kilowatt hours of energy to get it fully into its melt fraction. The temperature has only changed by 4 degrees C, but because it's changed phase, we now have, we're now storing 499 kilowatt hours in melt fraction. To extract that energy then, we take 1414 degrees C, we then connect our Stirling engine to it, and we extract the energy out to 499 degrees C. The temperature drops to 1410. What happens then is the silicon changes from a liquid to a solid, and then we go back into sensible heat again. Our cell will never go back down to 25 degrees C. It will stop somewhere around here, which is about 550 degrees C. So we will never be dealing with a cold cell. One of the interesting attributes of silicon is, as silicon sublimates or turns back to a solid, it increases in volume by 9.5%. This presents a problem with the vessel you're trying to store the energy in. And to get around this, you have to change the geometry. I'll just go back again. You have to change the geometry of the storage vessel to allow for this expansion and force the expansion into a vertical point. And you do this by putting a taper on your storage vessel. Okay, this is a graph of exactly what happens. We're putting energy in here, and after 13 hours from cold, we get to 324 degrees. Our temperature inside our cell, this is a 236 kilowatt hour cell with 10 kilowatts output. We reach 1450 degrees C. We switch off at that point, and we have a small amount of sensible energy here as our silicon goes back down to its latent energy point, which is 1414, and then our temperature drops down to 1410 at this point here, and then we go into sensible heat again. Our Stirling engines continue to operate down to about 450 degrees C, but we would normally start recharging somewhere around 550, which is down here. So our cells always remain hot. What does it look like? This is one we designed for a city bus. It's an 829 kilowatt hour energy storage. It gives us about 631 kilometers range. We're using 6 10 kilowatts Stirling engines. Here we have, sorry, I haven't shown a very good delineation between the graphite, which is here, and the silicon, which is here. But essentially, you've got 3 silicon baths or tubs stacked together inside an insulated vessel. The power output is 60 kilowatts. To that, we would use some of Dr. Sharma's supercapacitors. Supercapacitors are wonderful devices. They have very, very low ESR, very, very low internal resistance. What that means is that although they only store a small amount of energy, they have a massive amount of instantaneous power. And in a later slide, I'll show you how this operates. But the 60 kilowatt hours for this bus would represent 50 kilometers an hour, our cruising speed. Its acceleration and braking operate on a different cycle using supercapacitors and the motors in the buses operating as generators. This is a larger bus. This would be 1,596 kilowatt hour storage, 1,277 kilometers range. And again, the weight on this would be 7 kilograms or 7 tons, 7,000 kg added to the weight of the bus. In order to get this range, what we would do is the buses at the moment are made of steel. We would make the buses of engineered aluminium, reduce the standard weight of a bus from about 14 tons to 8 tons, and then introduce our battery. And this will give us this range of 1,277 kilometers. We've been talking to bus manufacturers, and this presents them with no problems. Okay, what does this look like? This is our unit we designed for proof of concept. What we have here is we've got 2 Stirling engines, one mounted either side of our cell. In the cell here, we have 255 kilowatt hours of stored energy. Each of these engines are rated at 10 kilowatts. That's 20 kilowatts output. And the device looks like this. So this here is a stationary unit, which we devised purely for demonstration purposes. And in 2018, we demonstrated this operating for Andhra Pradesh, for the government of Andhra Pradesh, and had a very pleasant evening with them. As I said, this unit has more in common with a fossil fuel power station than a battery, because it gives a constant output. It can be charged and discharged simultaneously. And under utilization, where we use it for a power station, we could size this up any size we want to. At the moment, we're looking at putting about 12 megawatt hours in a 12-meter container, and we can draw down 680 kilowatts instantaneous from that container. And what we would do is we would put multiples of these containers in, and if somebody wanted 1 gigawatt hour, we would just keep multiples of these containers to give us that stored energy. At the moment, the mathematics on wind and PV in unison only gives a shortfall of about 5 hours per day. What they're trying to do in South Australia here, what they've done is they put in 100 megawatts of lithium-ion battery. We would take this in a different format, in that we would put in, South Australia uses about 5 gigawatts instantaneous at peak demand. what we would do is put in a hybrid of supercapacitors and our cells, and then take the energy from wherever we can get it. So we're not designing the battery for the system. The system is designed around the battery. So the battery gives a base load power. As I said, how do we compare with what we're doing with what's existing? This gives you an idea of where we are. We're sitting at the moment here about 487 watt-hours per kilogram. Lithium-ion battery, which is down here with the Tesla battery, they're looking at 160 watt-hours. This is with a cobalt lithium-ion battery. If we go to a LIF PO battery, we're looking at much less than that. Sorry, we're looking at an output of about 90 watts per kilogram. At the time we put this together, we were looking at about $600. We haven't gone so much from that. This is usable cost into the grid. When you actually ask for what the costs are, it works out. This is with the ancillaries that need to be put to the lithium-ion battery, where our generators are generating whatever energy, whatever level of volts that's required. These are add-ons for lithium-ion. This is why the costs are much higher than ours would be. The round-trip efficiency on the lithium-ion is 80 to 90%. On some of the numbers I've seen coming out of the utilities, it's sitting somewhere around 80%. We're looking at 50 to 90%. We're looking at probably around 60% electrical, and if we're using the bottom end hot water in a combined heat and power situation, we will actually be sitting around 90 to 92% efficiency. Again, this is specific, as it is with power stations, to whether you can use the bottom end heat or you have to just convert that, just throw it away. The rest of the storage costs are fairly high. Red flow batteries, 40 watts per kilogram, probably marginally better than lead acid batteries. And again, the costs are fairly high on all of this. On levelized costs, because of the replacement of lithium-ion batteries, doing the same calculation we did, you're looking at probably about 10 to 15 rupiah, which should be in line with the calculations already been done per kilowatt hour. Oh, because of the change, the batteries would have to be changed every 4 to 5 years, whereas our battery doesn't. Okay, this is just to give you an idea of what happens when we use this in mobile. Now, when I say mobile, we're also talking to ship ferry manufacturers and ship manufacturers. And the problem with all mobile transport is that to get them up to speed, you need acceleration. To do that, using a constant output source like our batteries, which gives 80 kilowatts output, the time taken to get to whatever relative speed you're talking about would be far too long, 30, 40 seconds. So in order to get around this, I did a search 2 or 3 years ago of supercapacitors. Because of the high energy delivery of the high power delivery of supercapacitors, it matched exactly where our shortcomings were. And I reckoned if we could use supercapacitors, and at that stage I was looking at about 4 to 5 watts per kilogram. If we were using, say, 5 kilowatts of that, we could discharge 120 kilowatts on top of the 80 kilowatt standard. So we're now talking about 200 kilowatts to give us an acceleration of, say, 10 to 15 seconds to 50 kilometers an hour, ideal for bus and transport operation. What's happened in the meantime in the last 3 years, down to research, which I must compliment Dr. Sharma on. We're now looking at about 25 watts storage, which is absolutely remarkable. And what that means is that the weight of our supercapacitors now, from 5 kilowatts, which would have been half a ton of supercapacitors, we're now down to 100 kilograms. This is truly remarkable. Again, what that does is it adds to the range of these of the transport, whether it be buses, trains, ferries, or ships. It really is a remarkable development. Again, this is just to give you the maths that's involved in it. We're talking about the amount of energy during braking. If we were trying to put that into a battery, and I know it, I'm still driving a Leaf electric car, I throw away probably about 60 to 70% of my energy on heavy braking. So supercapacitors sort this problem out for us, no problem whatsoever. Looking at utility scale, for microgrid under Indian conditions, taking a dwelling in India, looking at about 3 kilowatt hours per day, using a microgrid with a 10 kilowatt cell at 255 kilowatt hours, we can supply up to 30 houses on a microgrid, and we can use the bottom end cooling in an absorption chiller for reticulated cold water for air conditioning. We can use the hot water in the mornings for showering or domestic hot water. And we can also give 3 kilowatt hours extra per day for charging a vehicle, whether it be an auto or a scooter. Probably not enough for charging an electric car, but at the moment I charge on about 6 to 7 kilowatt hours per day. So it would probably do a small electric car. One of the things that's happening with climate warming is that as the temperatures go up, the wet bulb temperature is getting above 33 degrees C for a number of, it's hitting it in a number of places in the world. Once it gets above 33 degrees C, this is going to cause a lot of angst among the population, because theoretically, if you will only last about 6 hours in this. So every house will need at least one room where they can cool themselves down. This is why I've been looking for absorption chilling, which is the cheapest possible method for having at least one room in the house that sits constantly around 24, 25 degrees C at a low humidity. So that's the reason that this was put in there. Well, that's it, folks. Again, thank you very much for allowing me to present to you. Where we are at the moment is because of the COVID virus, virtually everything has stood still. We're doing a lot of design work, but the actual physical production has stopped at this point. But hopefully, you guys are keeping yourselves protected from this virus, as we are in Australia. Hopefully, within the next 3 months, we will get back and start producing ourselves again. Again, thank you very much for your attention. Thank you.
Thank you. Thank you, Dr. Patrick. It was amazing, and basically it was well within the time scheduled. Thank you so much for that. And we have been getting some good feedback also from people. And basically I will put the floor open for questions. If there are any questions, we can take it up in next 10 minutes for the next 10 minutes. So you can just post the questions. Dr. Patrick is here to answer your any queries or any insights. Yeah, we are getting the thumbs up. It was amazing presentation.
Thank you. That's good.
Yeah, from people, from the audience. Okay, I think somebody is asking for the feedback link. Some of the few people are not able to find out the link for feedback. Dr. Parasar, could you help out on that? So people are asking for the link.
We can send some other time that feedback.
Yeah.
We have next session we can able to do it. But
Yeah, sure.
Okay,
some
I can answer the
important
questions
question,
later
so
on. It's not
that
a problem.
I am very happy that Patrick, you have given a whole glimpse of the energy scenario in the whole world, and in one slide keeping all the economy policy, all the things. So I am very happy. So what is your next generation plan? Energy storage challenges, how are you going to mitigate those energy storage challenges world is facing? So can you give some insight, some bullet points, so that our KIIT University and your company can make a international kind of forum? Because we have the
Great.
60,000 students are there here, so we have a main power, and you have some as an industry expert. In which way we can work so that
Okay.
can have
Yes,
a
sir.
real Atmanirbhar Bharat? Can you give some bullet points, sir?
Thank you, Dr. Weiser. Okay, where we are at the moment is we're dealing with silicon. Now, silicon has a melting point of 14 degrees C, and it's ideal for Stirling engines because they use an Inconel head, and it's fairly well matched. Inconel starts to melt about 1450. So once you can keep under those temperatures, you can just about get away with very high temperatures. Where we're going from this, we're looking at closed cycle gas turbines. And with closed cycle gas turbines, two things we can do. One is we can take the temperature using plasma torches. We can take the temperature up to 3,600 degrees centigrade to the melting point of graphite. By using ceramics, we can store this liquid graphite and put a heat exchanger through the graphite, which feeds into Stirling or feeds into closed cycle gas turbine. They operate under the Brayton cycle. So as we come off the compressor stage, we then push the energy through the heat cell at very, very high temperatures. We go up to the maximum temperature we can achieve on the turbine section, which at this stage we're picking will be around 2,000 degrees centigrade. And at that temperature, the Carnot efficiency of the setup will jump to about 98% efficiency. The second point on this is that because you're using closed cycle gas turbines, you can actually float the turbine shaft on molecular bearings or on gas bearings and use your compressor stage to float your shaft. Once your shaft is floating, it's now spinning on molecules of gas, so there is no friction. And theoretically, or by design at this stage, well, it is theoretically, we're looking at a set and forget situation where you could put one of these out in the field, zero maintenance for 20 years. Because the materials, we're living within the bounds of the melt and sublimation of the materials. There's absolutely no degradation. And the ceramics we're using have a very, very long life. So that essentially is where we're heading at this point. So what we would then have a virtually fail-proof device for storing very, very large scale energy. The other thing it does for us is it brings down the footprint. So instead of looking at about 480 watts per kilogram, we're now looking at 3 kilowatts per kilogram. So essentially we would be looking at a 12-meter container storing 10 times or instead of 12 megawatts, storing 120 to 200 megawatt hours of energy. So it reduces the footprint. But where this comes into play is if you're using it in shipping, you can now charge a ship for 12,000 kilometers in one hit of renewable energy and literally steam halfway around the world with it. So within the next 5 years, we're hoping to have the prototypes for this ready for testing. And with a couple of years after that, we would get into production. Does that make sense?
Yeah. Yes. Yeah. Dr. Patrick, thank you so much. And we have a lot of appreciation pouring in, indicating it is a wonderful lecture, educative, lot of information. And really, I thank you very much for taking out the time. Thank you, sir. And sir, any more questions? We have some 5 minutes available for some questions.
Great. Yeah, I'll be here for the afternoon. So yes, please. Thank you very much indeed for allowing me to present.
Rajendra sir, there is some question in chat box.
Okay, yes. But I'm not able to see over here.
Okay, so I can,
you
say the question.
Please, you please take up.
Sir, someone is asking, can we use lighting energy to store? What are the difficulties to get the energy from lighting and store? Lightning,
yes. Very good question. Probably more in Dr. Sharma's realm than mine. But for lightning, you need an ability to store energy very, very quickly. So what essentially you would do with your lightning rods, and again, Dr. Sharma can enlighten you on this, you would put lightning rods up attached to banks of supercapacitors. And as the lightning struck, your supercapacitors charge instantaneously, and then you discharge them over a long period of time through a circuit. So we can use it for charging our batteries, or we can use it for that. Do you want to comment, Dr. Sharma?
Yeah. See, basically, I would like to comment on that part. Like, the lightning part, when we call it, it is actually a bolt. One lightning bolt is having a current of more than 2 lakh ampere and voltage more than 20,000 volt. So if you multiply that thing part, and like there is a lightning arrestor everywhere which is installed. So if you install that lightning arrestor through a supercapacitor, of course it has to carry the supercapacitor has to be of that voltage. Okay, then definitely you can arrest that part in that supercapacitor, and roughly with one lightning bolt you can supply for 6 months to half of Pune city, right? But the capacitor will be very huge. So practically it is something different, but theoretically, yes, it can be done. But because on thermal battery, it cannot be done. It can be done on supercapacitor because you have very short time and you have to capture that energy within that fraction of second. Thank you.
Thank you for your question.
Ma'am, some more questions?
No, sir, there is no more questions.
Okay. So I think, thank you, Dr. Patrick. Thank you so much. And looking forward to see you soon in India. And definitely on behalf of Dr. Parasar, I would invite you to KIIT also. It will be a pleasure to have you over there whenever you come to India. Thank you so much.
Great. Looking forward to it. Thank you, guys.
Thank you.
Yeah.
Yeah, Dr. Parasar?
Yes.
Yeah. Okay, Dr. Patrick, you can do that stop sharing part. So your screen will get, there is an option, stop sharing.
Stop sharing.
Great. Yeah, thank you. Thank you so much. So our next person is Dr. Balram Sahu. Is he available? Has he logged in, sir?
Yes, sir. He is the co-host.
Okay, fine, great. Because I'm not able to see on screen, so I'm sorry for that. So
no problem.
Yeah. So I think we can go ahead with the next part. And I'm happy to introduce Dr. Balram Sahu. He is an associate professor of IISc Bangalore on Material Research Center. Dr. Balram Sahu also holds a PhD in natural science from Germany. He has done his postdoctoral on environment science from Switzerland and another postdoctoral on photon science again from Germany. So, and basically he has done MTech from IIT Mumbai, and definitely you can see his MSc Physics from Utkal University from very own Bhubaneswar. He also happens to be a member of societies like Indian Ceramic Society, the Magnetic Society of India, the Material Research Society of India, and also Electrochemical Society of India. Dr. Sahu is having over 120 publications, and he is also an associate editor for journals of electronic material, and also he is on the reviewer panel for many journals like ACS, RSC, Elsevier, Springer, Wiley, etc. So it is great to have him over here. His research interest is in the domain of nanoscience, surface and surface interface science, X-ray and photon science. So definitely it will be a very informative and good session with Dr. Balram Sahu. So sir, we welcome you on behalf of AFM 2020 and KIT. Sir, the dice is yours. You can take over. Thank you.
Yeah, thank you very much. And it's very nice. And it's also my great pleasure to be here speaking in front of all these exalted personalities. Do you hear me properly?
Yeah, yes, sir. We can hear you.
Yeah,
So you
okay,
can go ahead. Yeah,
that's very nice. Yeah, thank you very much. Yeah, so today's presentation is, I have changed the title a little bit, but it is the same information that I am going to convey here. And the information, if some doubts or some questions arise, even after the talk, you may email me to my email address that's given here. So this work that I'm going to present today is majorly carried out by my PhD student who is already graduated now, Rajiv Kumar. And there are other group of students who are working with me also, and they have helped also in this work. And this work is basically a collaboration with Professor Rezi Philip from Raman Research Institute and his group. And in this talk, I mean, before speaking about how to enhance the nonlinear optical absorption property of the materials, maybe I will give a brief introduction to what actually it is. What is nonlinear optical absorption and why do we need it for? And here I have shown the spectrum of electromagnetic waves that's possible. And on top of that, there is one depiction of a polarized electromagnetic wave. And the polarized electromagnetic wave has electric field vector and magnetic field vector. And those are oscillating. If it is polarized, it's they are oscillating in a plane up and down, like it is depicted there. And when we say about the normal or ordinary light, the waves or the photons, those that are coming out from the ordinary light, are not coherent. As it is not coherent, we have very low amplitude at any point when we see. But in case of lasers, because that is designed in that way, all the waves that come out from laser are coherent to each other. And because of that, we have very high amplitude or high intensity there. So this high amplitude means the electric field that is created at any point is very high. And yeah, so this electric field we can use to transport electrons from valence band to the conduction band in case of normal materials, if it's insulating. Or also we can use this electric energy to move the electrons in the conductors also. And the semiconductors are in between. So depending on the band gap and the energy of the light, the photons, that can absorb the light and can go to the conduction band and conduct. So this is the way when the electrons observe the light that we incident on the materials. And after absorption, the electron that goes to the excited state will try to come back to the ground state. And in this process, it has to satisfy the energy and momentum conservation rules, and to satisfy the momentum conservation especially, because there are many different ways available to satisfy this energy conservation, momentum conservation rules. This photon that will come out will be spontaneously coming out in any direction wherever it wants, or depending on the momentum conservation that's occurring there. However, if the electron is in the ground, in the excited state, and you incident another photon onto this electron, it will start to oscillate this electron along the direction of the oscillation of the electric field vector. As a result, you will see both photons will come out as it is depicted there. Both photons will come out in the same direction and having the same phase, and they are coherent to each other. In this way, we can increase the intensity of the light, and this intensity of light, increase in intensity of light, will lead to some kind of nonlinear phenomena. So whether it's absorption, if it is absorption, as you can see here, the right side picture, you can have, let's say, if the energy you provide is, let's say, omega, S cross omega, and that can take this electron to some excited state. And if that excited state doesn't exist, it is just a virtual state, then if another electron is present at that point, sorry, another photon is present at that point, then that photon can take the electron to another virtual state. In this way, this electron can go to higher and higher energy virtual states. And then when it comes back, it will directly come back, because there are no actual states in between. It will directly come back to the ground state. As a result, you will see the second harmonic generation, or in this way, you can have third harmonic generation, and the expression that describes this is given on top. So if you have electric field of the electromagnetic wave oscillates in this way, E0 sine omega t, and if you have a nonlinear polarization, this way the electron is going away from this nucleus, so that we have polarization, and this polarization will be having nonlinearity, and that we can express in terms of the nonlinear susceptibilities, as it's given in the equation on the right hand side. So here you can see the omega term is there. Then there is a constant term. That constant term is the optical rectification, and the omega term is thus the transmitted light, or the ordinary light that will be coming out. That's a linear absorption or linear emission. And then we have second harmonic generation, that is cos 2 omega term is there. And all this way, I mean, when you expand the P or chi, that will be giving you second harmonic, third harmonic, like that. And in this process, you will get all different energies. I mean, you can tune different incident wavelengths, and you can get all different energies that you need for different applications. So here, as I discussed, you can use the nonlinear phenomena to generate photons of different energies, and those can be useful for, I mean, in different laser devices, and you use laser devices in different applications. And on the other hand, when you have a high intensity laser, if that comes to pulse on our body, then that's dangerous, and we should protect it. And in this case, we need to consider how to protect ourselves by using this absorption of photons. And in this way, the laser safety is a very important aspect, and we can achieve that by using developing proper materials which can observe these photons, which are very high intensity, coming at a high intensity, and that there we have to use the nonlinear optical absorption. And that's what I'm going to present today. So when you see there are different aspects of laser safety, but let me tell you what actually linear absorption of light in materials is. So when, let's say, we consider a piece of material as it is given there, and we incident a light, beam of light, and then a part of that light will be reflected, and it's possible that part of that is transmitted, and part of that will be absorbed. And this absorption process is basically depends on the material properties. So we need to consider the epsilon, that is the dielectric or permittivity of the material, and also the permeability, the magnetic part, because when we incident electromagnetic wave, both electric and magnetic field vectors, they will interact with the material electric field and the magnetic field. And in this way, we have, the absorption process taking place. But when we have intensity of light is not very high, in that case, we have linear absorption. And we already know the Beer-Lambert's law. Those are already quite old, and I think everybody knows that. And this process absorbs the light, and I have given here how the intensity falls off as the distance inside the travel distance of this photon beam inside the material proceeds. So on the right hand side bottom that you can see there. But that's all about the linear absorption. Let me tell something about nonlinear absorption. As I told you, in nonlinear absorption, we have very high intensity light. And when we have very high intensity light, as I told you already, when you have one electron at the ground state, as you can see on the right side picture or bottom picture, both are similar. So when you have linear absorption, then one photon is sufficient, has sufficient energy to take the electron from the ground state to the excited state. As you can see the left side picture of the bottom one. And then after it is excited, that electron comes back to the ground state, and that emits the photon. That's the emission process. But the absorption process here is a single photon absorption. One photon absorption. But if the energy is not sufficient and the intensity is very high enough, in that case, we can use two photons. Let's say one electron is there, as you can see on the right-hand side of the bottom picture. The one electron is there on the ground state, and that gets this energy of the photon and takes the electron to some excited state, which is not sufficient to take the electron to the excited state completely in the upper side. That is the, let's say, conduction band. But in this case, you can use two photons. If the intensity is very high, then the one photon that takes it to some virtual state, and another photon is present at the same time that can take the electron to the excited state. In this way, you can have two photon absorption. And three photon absorption is given there on the top picture. Three photon absorption, that's possible. And on the right hand side, it's given when you have three photon absorption, if the state is not actual, if it is a virtual state, then the photon will not be staying there. There will be no absorption, but it will come down to the ground state by emitting this 3 omega photon. But it can also be possible that there are states in between. Then you will have different other absorption processes. Those are listed on the left-hand side that you can see. We have two photon absorption, three photon absorption. You can have also saturable absorption. And we have excited state absorption. Excited state absorption is basically when this photon takes the ground state electron to some excited state, and the other electrons, other photons which are present on the there, they can take the electron which is in the excited state to some other excited state, whether it's virtual or actual. Then we can have also pre-carrier absorption. Pre-carrier absorption takes place mainly when you have pre-carriers present in the material, basically in metals. So when you have metals, these free electrons, they will take this energy and they will go away somewhere. They will not be stay there. So in this process, you can observe the photon. That can be also nonlinear absorption. Then, let me give you the main theme of this talk about the nonlinear absorption concepts and choices of materials for advanced technology. So in this case, I'm going to tell you 5 different materials which we have used to explain all these concepts that I have already told you, and different materials we have synthesized. So maybe I will just give you a short brief introduction. What are the materials? In the first case, we have used iron-based materials. So iron and carbon. Okay, maybe we go to the next slide, so that will be clear one by one. So in this case, we used some yttrium iron garnets, and we doped aluminum in that. When we dope aluminum in that, then we have change in band gap, or you can see here when YAG is the yttrium aluminum garnet, and when we dope in iron in that, the band gap decreases, as well as there are some defect states introduced on the surface of this material. And the defect states, they will just broaden the edges, the valence band edge and the conduction band edge. As a result, you can have also actual levels introduced there. As a result, this facilitates the excited state absorption process. So if someone wants to know more about these aspects, one can see all these references already given there. And the other type of material that we have used are basically carbon nanotubes or carbon globules. The carbon globules are basically the structure that you can see here on the top. So the globules, those are basically amorphous carbon. And within this amorphous carbon globule, as you can see on the right-hand side of that top picture, there are some black spots. And those black dots are basically the metallic particles. And around these metallic particles, there is a graphitic layer created because of our deposition process. And that's what I'm going to explore in this talk, so that one can understand what are the parameters one has to control in order to increase the nonlinear absorption. So we have prepared different materials. Those materials I am going to show in the next slides. So that's why I will not explain all those, but if someone needs to go into the details of this synthesis process, then one can use or one can go through the literature that I have listed here. We have also other literatures related to this work, and you can go through that as well. Want. So the experimental method, how do we really determine this, the ability of the material to observe nonlinear in a nonlinear process, they observe the photons. That's given here. We have on the left side, when you start, we have a laser, pulsed laser, that is focused onto a sample, which is given in the middle of this, and the sample will be moved or is moved from left side to the right side. And when the sample is at the center, at the 0 position that you see, the intensity it receives is very, very high. And when it goes towards left side or right side, either way, in both directions, we have decrease in intensity. In this way, when we scan the sample, then we get different intensity of the photon, and we can understand what happens to the nonlinear absorption. So there will be linear absorption also, but by using the equation given there on top, one can eliminate the, we don't need this linear absorption part. So we consider only the nonlinear absorption part. And when we plot that, you can see here on the right bottom picture, we have the Z scan, and at the 0 position, we have more nonlinear absorption because here it's plotted transmission. Transmission is lower at the bottom, sorry, at the middle 0 position. That's where we have more absorption there. So in this way, maybe I'll go to the I'll just show you the reference that we have used, how we have done the measurement. So that sample we have seen on the previous slide is basically a combination of ethylene glycol and the other materials that we have used. And both this dispersion of this sample and the ethylene glycol is put inside one of the capillary, and that capillary is put there in the instrument, and then that is scanned. But the ethylene glycol that you can see, there is no absorption. So that's why we have used the ethylene glycol as a reference sample, so that whatever information we get from the sample. This is the procedure. We don't need it. I will not explain it now. So let me tell you what are different ways one can control the nonlinear absorption in different materials. So here in the first case, we have studied how to control the two photon absorption, 2 Pa, 3 photon absorption, 3 Pa, or the excited state absorption in different materials. So in this case, you can see here, as I already told you, we have used here yttrium iron garnet or yttrium aluminum garnet, and we dope in either aluminum or iron there. And in this process, when we dope in, we create some defect states, as well as the band gap is changing. And that's what is helpful in nonlinear absorption. That I will explain it in the next slides. So here we have synthesized the sample. You can see the formula on top. Yttrium, iron, aluminum, garnet, and X is the aluminum content. When you put in aluminum, or the other way also, it's possible. We go from yttrium, iron, garnet to yttrium, aluminum, garnet. And when we have different compositions, we have different band gap and different defect levels there within the band gap. So here we studied the structure and the cation distribution. Aluminum normally goes to the tetrahedral side. When it goes to the tetrahedral side, and it has also smaller size, the ionic radius. Because of that, you can see on the right hand side the A value, the lattice parameter, that decreases as we increase the content of aluminum. And in the next slide, you see we have, the same information, the cation distribution and the magnetism is studied. This says that the material is well characterized. And then the other point that you can see here, the size of the morphology, or the SEM image that you can see here, the morphology tells that the structure in all cases, all the samples, we have coral shaped morphology, and the size of these branches, coral branches, those are varying. You have yttrium iron garnet that has the biggest coral branch, and yttrium aluminum garnet that has smallest coral branch size. And this way we have characterized, and the change in band gap that you can easily visualize from the change of the color of the samples that is shown here. And we have studied also the using UV visible diffuse reflectance spectrum or spectra. We have studied what is the band gap and how the defect levels are distributed within this band gap. And that you can see here, the band gap is very large for the yttrium aluminum garnet. That's about 6.5 eV. That is not observed in this picture here, but the others are observed. So this value we have taken from the literature, 6.5. But the other values that you can see easily, as you dope in more and more iron, then the band gap decreases. And there are different amount of defect states introduced, and those defect states can be understood by using the Orvac energy. Orvac energy actually tells you how much spread of these defect levels are there into the band gap states, band gap region by this introduction of iron or aluminum into this garnet structure. And then we have studied the materials by using this Z-scan technique, the nonlinear absorption behavior. And you can see here on the left-hand side, I have on the right-hand side, the band gaps are listed. And then we have the nonlinear absorption, those curves you can see easily, the transmittance versus Z position in micron. And then you can observe here, as you go on increasing the or decreasing the EG band gap, the nonlinear absorption goes on increasing. So this tells us that as the band gap decreases, the process, I mean, if the band gap is very large, then you can have 3-photon absorption process. So when you have 3-photon absorption process, because this absorption process involves virtual states, not actual states, so you have very little absorption there. But when the band gap decreases, then 3-photon absorption process goes towards 2-photon absorption process or 1-photon absorption process. And when you have 1-photon absorption process, we have excited states also involved, which are actual excited states. And in this process, one can increase the nonlinear absorption process in the material. So this tells us that when we go from, let's say, 2-photon, 3-photon absorption process towards excited state absorption process, then the nonlinear absorption phenomena or the nonlinear absorption process becomes very prominent in these materials. So let me tell you, I mean, if you need to understand more, you can go through this paper. Let me go to the next set of materials. So there, here we have used so this carbon-based materials that I have told you, and there we control the graphitic cell thickness on the metallic particles there. And when we change the graphitic cell thickness, you can understand the density of states in the available density of states which are empty, or the density of final states for the transition, those will be higher. So when the density of states becomes higher, the transition probability becomes higher also. So in this process, one can increase the nonlinear absorption behavior. So to do that, what we have done, we used, I mean, this is the furnace that you can see, and the temperature profile is given below. And there is a tube inside, and that is quartz tube. And at the end, the closed end of this quartz tube, we put some the precursors. And here we have used iron acetyl acetonate and toluene. Iron acetyl acetonate is the precursor that helps in growing these graphitic cells. When it forms this iron particles there. We'll see that in the next slides. So here we inserted this tube into the furnace at different temperatures. That's given here as T in room temperature 300, 400, 500, 600 degrees Celsius. And we carried out this pyrolysis method or pyrolysis at 950 degrees Celsius for 12 hours. In this process, what we observe is you can see the particles there. So on the left-hand side, you see the ACM pictures. So there are more or less many nanotubes present. And on the right-hand side, you can see the right-hand side middle panel. You can see the black one is the iron particle. This is basically Fe3C, it forms cementite. And on top of that, there is this, in the first picture, there you see the graphitic cell is not well crystallized, but when you come to the next one, the 300 case, when we insert that 300 degrees Celsius, that is very well crystallized. And the lower one, you can see it's very little thickness of this cell. So as a result, you can see the density of final states one can expect that for the well graphitized and the thicker layer will be higher. And this is what we have also observed. I mean, there are other characterizations. I will skip those to understand clearly whether it's whatever we have done, it's really believable or not. So you can go through the paper. I'll give you the link there. So here I'll just tell you what happens here is actually we can see here as you can see here, the amorphous carbon on the right hand side picture that you can see, amorphous carbon doesn't observe anything. So all the absorption that will come from the cementite and the graphitic layer above the cementite particles. And you can see here at about F equals the T insertion at about 300 degrees Celsius, we have very large absorption of the electromagnetic wave or the photons, laser photons. And that's what is very important to understand that we have found out the band gap involved there that you can see here. Band gap in all these materials are more or less similar. It doesn't vary very much, but the defect states that you can see from the tail that is emerging out, the defect states are varying in different materials. And we have calculated the defect states that you can see here. And that actually matches with our the expected results that the F300 has a very nice graphitized layer, and the other cases when it's at very low temperature, at very high temperature, in both cases we have more defects, and that's not good for linear absorption here, because the final density of final states will not be that high. That we can see it here. We have the final result. You can see when you have well graphitized cell on this side of Fe3C particles, we have very high absorption, about 40% transmission, or yeah, the 60% absorption there. And in the lower one, when you have a smaller cell thickness, that is obviously lower, that you can see. Yeah, so one can see this, we have some publications, so one can go through that. So let me tell you what happens when you change the degree of graphitization. When you change the degree of graphitization, that means we see this graphitized layer on top of this metal particle, and we varied the defect concentration in this materials by using the technique of taking different amount of precursors in the quartz tube. And by that, I'll just show you the results that you can see. When you have different amount of precursors, the size of the metallic particles are lower, and as a result, we can have also the graphitic cell that develops has a different amount of defects. Those characterizations that you can see it easily here. I mean, on the right hand side picture that you can see, that is that belongs to this is the XRD, and that is the zoomed in image, and the one which is at about 26 degrees to theta value, for about 100 mg of this precursor, we see very sharp peak there. So this means the graphitic layer is very well crystallized, and the defect amount is less there at about 100 mg. But in all other cases, it's less, and that's what we have also studied in this by Raman and other methods. But I will just show you the result. In this case, you can see the for about 100 and 250, basically 250 has very high absorption there. And one can also see in this case, when you have 250, it's not only the density of final states, but also the amount of defects present there, because the amount of defects, as I told you, they introduce defect levels within the band gap, and that helps in increasing the excited state absorption of the nonlinear absorption of the laser photons. And that's what here you see it again. We have amorphous carbon. We designed some experiment, and we got some amorphous carbon material. For amorphous carbon, there is no absorption. Yeah, and then we have also studied the defect amount and the defect levels within the band gap, that you can see it here. When you have a different defect amount, different structure we have, and electronic structure, and then that leads to different absorption. And here we incident different amount of photon energy, the input laser energy, it's not photon energy, the laser energy, then we have different absorption process that we have studied. But I will not explain more about that. If you need, you can go to our paper, and that's you can understand it more. I'll just tell you, because lack of time, I'll just tell you what we have studied here is you can see the defects present within the graphitic cell. So here we have cobalt particle, and above the cobalt particle there is a graphitic cell, and the graphitic cell we have different amount of defects. When you have different amount of defect because of different amount of defect levels introduced within the band gap, we have different absorption process. As a result, we have different absorption for different materials. So that means by controlling the defect states within the material, we can enhance the nonlinear absorption properties of the material. So quickly, I'll just go through a few slides. So here we have studied what happens when you have pre-carrier absorption process in there. That means the metallicity of the nickel particles in this case, or the particles which are used for this nonlinear absorption, for this synthesis process, they also help in the nonlinear absorption process. Here you can see, I mean, I'll just go to the results. So here in case of nickel, we have more absorption, but when there is a nickel oxide layer, then the metallicity decreases. When you have metallicity decreases, in that case, there will be no precarriers going away from this nickel particle, and they are not also transmuted in the graphitic layer. So as a result, you will have very little absorption process that you can see on the right-hand side picture. So maybe I will skip all this because lack of time. I'll just go to the yeah, so we prepared it this way. So we have different heating rates we use, and because of this change in heating rate, we have different samples. They differ in their morphology. On the left-hand side, you can see when you have very slow heating rate.
Balram.
Yes.
Hello.
Yeah. Yes. Yes.
You can take time and explain nicely. Okay, we have time. We have.
Okay. Okay.
We have time. You can explain nicely.
Okay. Thank you, sir. No problem. Yeah. Okay, so here you can see, maybe I'll start it here. When you have very slow heating rate used there, you can see when you have very slow, let's say 1 degree Celsius per minute, then the graphitic cells, those are not well developed, and the metal particles are also smaller. And you can go to the 3 degrees Celsius per minute, the left bottom curve, and the particles there, you have very nice metallic nickel particles, and also very good graphitic layer surrounding it. And when you come to the little bit higher heating rate, along with those particles, with the graphitic layer surrounding those particles, we have some nanotube structures coming into picture. And those nanotube structures become thicker by some amorphous carbon layer when you have 20 degrees Celsius per minute heating rate. So those are well characterized, and maybe I'll show it there in this picture here. So you can see here we have nickel particles smaller on the top, and when you go to the middle one, it's a little bit better nickel particles, and the graphitic layer is also better, that you can see on the right hand side. And when you go to higher and higher heating rates, then the graphitic layer becomes better and better, but you have some nanotubes coming into picture that you can see on the left side picture. Okay, so this process we have used to synthesize the samples, and we have measured the nonlinear absorption, and you can see it here when you have the nonlinear nickel particles, when they are smaller and they have smaller graphitic cell on the top one, 1 degree Celsius per minute, then you don't have very nice absorption there. But as you increase the heating rate, then there are more and more graphitic layers, and as a result, you have better and better absorption of the nonlinear absorption of the laser photons, and the absorption becomes very good when you come to the about 3 degrees Celsius per minute, and at about 10 degrees Celsius per minute, this is more or less similar. But when you go again to higher temperature, higher heating rate, 20 degrees Celsius per minute, then it again absorption becomes less there. So what it tells you, so this explains some dependence on laser intensity. So I'll skip that, but you can see it here. What happens? Maybe I will show you the Raman spectra that we had. Yeah, here you can see on the right hand side picture. On top, it's the full Raman spectra, full range of measured Raman shifts. But the most important is the left side peak that is shown with a dotted vertical line there, and that is zoomed in the lower picture. That you can see for the 20 degrees Celsius per minute heating rate, we have a broad peak that correspond to the nickel oxide Raman spectrum. And this nickel oxide is very little present in the other samples. So this tells us that the nickel oxide or nickel particles in 20 degrees Celsius per minute synthesized samples are very, non-metallic type. In other cases, it's metallic. So this tells us that what actually happens when you have metallic and non-metallic particles. When you have metallic particles there, that you can see, as I have given you here a cartoon, we have nickel particles which are metallic, and the graphitic layer which is also metallic. So when the incident laser beam comes, that excites one electron from the nickel particle, and that electron travels in the nickel particle itself, or it can go also to the graphitic layer present there. When it goes to the graphitic layer, it can be carried away by the connecting graphitic layer in the nanotubes. So this is the process in which this nickel particles with graphitic layer and the associated nanotubes, they help in increasing the nonlinear absorption process there. But when you go to the next picture, as I have depicted in the middle one, when you have a nickel oxide layer, that actually polarizes. When it polarizes, it doesn't allow the electrons to pass through. And if it doesn't allow, then it will not absorb the photon. And as a result, you will have very little absorption there. And that's what the main finding. Maybe this is how we explained by using the energy level diagrams. Maybe I will skip this part. So this is what I told you, and if you are more interested, you can go through our publication there. Let me go to the last few minutes. I'll just explain how we can use all these different aspects, what I have explained, how to introduce different energy levels within the band gap, how to associate the graphitic or the carbon nanotubes with the metallic particles, so that we'll have FCA, the pre-carrier absorption. We can have excited state absorption. We can reduce the 2-photon or 3-photon absorption by decreasing the band gap. As we have seen, normally in this carbon-based materials, the band gap is not that high. So in this sample, we have explained everything that I'll tell you. So you can see here on the top, we have some carbon nanotubes, and at the tip of this carbon nanotubes, there are some metallic particles that you can see in figure B, on the left-hand side, figure B, right-hand side of the left figure. And this metal particles, those are metallic. And as you can see in the previous slides, previous samples, when you use nickel normally it doesn't leave this oxygen out. So we didn't use nickel here. We use iron, cobalt, and chromium. So this is very good, forming very good metallic particles. And we have bamboo-shaped carbon nanotubes attached to that. So as a result, because of this carbon nanotube and the metallic particle, the carbon nanotube and the metallic particle, along with this metallic particle, we have a graphitized, well graphitized layer on top of this metallic particle. So all these, they help in increasing the nonlinear absorption process. The metallic particles, they help in increasing the nonlinear absorption via, as I said, pre-carrier absorption, and then the graphitic layer that observes the nonlinear absorption process, observes the photons through this excited absorption process, and a combination of the metallic particle as well as the carbon nanotubes that helps in pre-carrier absorption, but it's an interconnected pre-carrier absorption process. In this way, we have very, very high absorption achieved. In this case, as you can see in the lower figure, it's coming about 20% transmission, so about 80% absorption there. That's we have explained it by using by other characterization techniques. So all this supports our claim that these materials are very good for direct application of in different devices as laser shield materials by observing the nonlinear photons. So this is what I wanted to tell in this talk. If you are interested more to read about the last part, that's already also published, that you can go through our publication. So in summary, I just want to tell you that the science and technology that I have already discussed, how to control the synthesis parameters in order to obtain very nice materials, which are very good for enhancing the nonlinear optical absorption, especially using the carbonaceous materials. I didn't talk about the other advantages of carbonaceous materials, but those are, as you know, those are very good materials. And then we have, I have shown that nonlinear optical absorption in carbonaceous materials is really excellent. And then those materials can be directly used for laser safety application. So with that, I like to thank you all. And I thank you all for your patience. And I like to thank all the organizers and the everyone who is involved in this conference for this beautiful conference. Yeah, thank you very much. If there are any questions, please go ahead.
Thank you very much, Dr. Balram Sahu. It was a very insightful session, and there are questions now I'm able to see. Okay, so one of the questions from Lipsa Misra is like, what are the Taut region and what are the Arbach region and the weak absorption region? What is the difference between this?
Okay, so let me go to one of the slides. Maybe let me go to the first part of the talk. Yeah, here let's say. We will go to the next. Okay, here. So you can see, let's consider any one of this UV visible diffuse reflection spectrum.
Yeah.
Let's take one in the middle, let's say the pink one that corresponds to YAIG3. In this case, you can see the reflection is increasing in this case. So if a reflection is increasing, it means the absorption is decreasing. So the highest absorption is occurring, let's say the highest absorption that we see at about, let's say, how much it will be, around 350, yeah, around 350, where it's saturating almost at the lower part. And there is a sharp increase in the, from that point, there is a sharp increase in the reflection. And where the sharp increase in reflection there, so that means the absorption decreases when the wavelength is lower and lower. So when we plot this in terms of absorption, it is the next one. So that is, this is not actually the Tau region. because talc plot is basically you get when you directly measure the absorption, but here we measure the reflection, and from reflection we calculated what is known as the Kubel-Kammung function, and Kubel-Kammung function tells us what is the band gap. When you plot it, a Kubel-Kammung function is somehow proportional to the absorption coefficient alpha that you see in talc plot. So here we plotted FR h nu omega h nu square versus the energy. When you see this energy, the sharp increase in the absorption that you see, that actually tells you where the, where this sharp straight line part intersects with the x-axis is the point where the absorption takes place very sharply. So that means the band gap will be where this the pitted line or the line that intersects the x-axis. So that is the band gap. But you can see here below the band gap energy, there is a tail in most of the cases, but it's high when you see YaIg1 and YaIg2, 3. So all these are there. So you can see here this tail that tells you, even if the band gap starts at a higher energy, below that energy there is some absorption also, and those absorption is basically the defect states present within the band gap, and those defect states helps in observing the photon, and the band gap, in that case, below the band gap, the absorption is also taking place. So this below the band gap, whatever absorption takes place is the Orbach energy, Orbach range. And the tau range is basically the straight line region that you see in these plots. That is the tau range. Yeah. So I guess it's clear.
Yeah.
So here the Orbach energy also one can plot it, but I didn't talk about that. Yeah, I guess that's clear. Yeah.
Thank you, sir. And one of the audience wants, his name is Bhavesh Dadij. He wants to know whether, sir, you have observed any saturable absorption.
Yes, we have observed.
Okay.
But I have not discussed it more. Maybe I'll tell you in brief.
Yeah. So we can ask the person to get in touch with you.
Yeah. Okay.
Something regarding that. Yeah. Sir, there is one more question from Subrat. They want to know how the band gap of CNT changes with Ni and Zn by nonlinear absorption.
How the band gap changes?
Band gap of CNT changes with nickel and zinc by nonlinear absorption.
The band gap of the CNT as such doesn't change.
Okay.
But yeah, the nickel particles, they help in in the development of different nanotubes or different graphitic cells because of the different property of this nickel or cobalt or other particles. They get some different amount of defects. As a result, there are defect levels, and that can seem like the band gap of the nanotubes or the band gap of the whole material changes. It's not only the nanotubes or the graphitic layer. So whatever we study here is the whole material.
Okay. I think it is answered. Thank you. And there is one more question from Lipsa Mishra. Can we differentiate the ESA and the free carrier absorption in the transit absorption?
Yes, one can. That's what we have differentiated. When I saw that, maybe I'll put the slide again. If you have both present at the same material, it's very difficult to distinguish. But when you have different materials, then it's easily you can say what happens in what. So here you can see here, when you have free carrier absorption, when you have nickel particles, then there is a more free carrier absorption because nickel is metallic. But as soon as you have a oxide layer or some oxide particles inside this nickel, then the free carriers, they cannot move easily. So as a result, you'll have very little absorption there. So when you have different samples, then you can easily distinguish. But if you have the same sample and both are happening there, like in the left side picture, from there you cannot easily distinguish from this single measurement. But you can prove it by doing other measurement, other characterization techniques that you have both are involved in this process of absorption.
Okay. Thank you, sir. And the same viewer wants you to elaborate the next slide. I mean, slide number 70. The next slide.
This one.
Yeah, yes, sir. Thank you.
Yeah.
Yeah.
Okay. It's a long slide. Okay. I'll just tell you. So what happens there? Maybe this is the depiction in the past in figure A. We have the valence band and the conduction band. And we have electrons in the valence band. And by observing a photon, it can take the electrons from the valence band to the conduction band. And that's what is shown as 1 Pa. And once there is this is the excited state, once the electrons are there in the excited state conduction band, the other photons which are present at the same time, and the same place, they can take the electron to higher states. So this depicts that how this excited state absorption takes place in the material. But the next picture close to that tells you, in case of metals, it's not actually overlapped conduction and valence band. They are very close to each other. They should be overlapped. But for basic understanding, it's very close to each other. So in this process, this in the right side picture, the electrons, they can go to the upper the conduction band and they can conduct. And it's possible, as in our materials, these electrons which are in the, because the particles are confined within this carbon layer or the graphitic layer, these electrons, they normally go to the carbonaceous layer. So this can happen by observing a photon, or if depending on the position of this conduction band electron. So it can come directly to the excited state. And then in this process, this electron can be carried away to other parts of this carbon nanotube if it is present. So this basically depicts everything what I have explained. And in the other three pictures, those are basically tells you individually what happens in different samples. So let's say in case of a B, that corresponds to the 250 and 1 degree C per minute synthesized sample. So in that case, very small particles. And in this process, we have one photon absorption and excited state absorption. And also we have the electrons coming from the nickel metal particle on the right-hand side to the excited state of the carbonaceous or the carbon nanotube or the graphitic layer on the particles. So the bottom one is again similar, but the process occurring there is different. So the red highlighted region, the text that tells you what happens there. In the past case, we have high excited state absorption, low FCA, because these particles are very small and they are well separated, and the graphitic layer is very thin. So in that case, we have low FCA and moderate ESA in case of the particles there. But when you come to the other samples, 3 degrees Celsius per minute or 10 degrees Celsius per minute, in this case, both or all different absorption processes becomes very strong, because the nature of the sample that tells you that. And in the last one, as you saw, there is nickel oxide found. So there is no transfer of electrons from the metal to the excited state of the graphitic layer, or vice versa. So that's why we have very little FCA, and that explains in terms of the energy level diagram. I guess it's clear. One can see the publication we have.
Correct. And thank you, Dr. Balram Sahu. In fact, thank you for this detailed, elaborated explanation. Thank you so much. And I think there are we can do the concluding part. And thank you so much,
you.
sir. I will
Yeah, thank you.
hand over
Thank you.
to Dr. Parag, sir. Thank you so much, sir. Yeah.
Okay, thank you very much. And I also thank all the
Thank you.
organizers and you too. And also, I mean, all the participants for their patience and listening and comments. Thank you all again. Yeah.
Thank
So
you.
thank you very much, Dr. Balram, giving a very nice presentation and enlightened the audience, and myself also enlightened by sharing the
Everybody is enlightened, sir.
calculation and measurement of the band gap, and the whole world is struggling in the band gap tuning. Whole world, and this is a big challenge. How you can twin the band gap. So really, you have given a very nice focus, and I feel the student definitely learn the way the question asking. This is a real conference, as I can say, when a student asks the questions. And special thanks to our on our behalf organizing committee, Rajan Sharma. He is so much busy, and he busy schedule in so much ministry meeting, another meeting, industry meeting, whole night. Probably you don't know when I call him 3 o'clock night. Also, he is working. And a special thanks to Dr. Patrick. Even though I'm not able to connect by WhatsApp message, we are able to connect it just to see the digital things. Morning I given message, Rajendra connected him, and he's given the whole world in one slide. The whole world is struggling in the energy crisis, and I can say in advanced calculation, I can say these two leaders, Rajendra and the Patrick, are the real energy leader in the whole world. If you go in the website, other things, and they are the lead, they don't say, but if you go in survey of the and the industrial survey, they are the top leader. And surprised to know that Rajan Sharma is associated with the KIIT University, and we are that level, the world leader in sense the energy storage. And our India Prime Minister is also focused on the nano missions and others about the energy storage, and given very right clear picture how we can lead. So definitely this Dr. Patrick connection is going to happen with our KIIT University. Rightly told Rajan Sharma on behalf of our organizing team and me. I am very thankful, sir. You already connected to Patrick, and he's also, I hope he will not deny to be associated with the KIIT University. And in the future, definitely we are going to do some mega event in terms of industry, so that our KIIT students or other people of the India can have some kind of employment generation. Thank you very much chairing the sessions, and I hope we can have the lunch now. We can meet at 4 p.m. today. The first due to
Thank you, sir.
some medical problem, he is not able to available. So 4 p.m. today we're going to meet. And today there's a 5 continent people are going to meet today. So this is a wonderful talk today going to happen again after the lunch. 5 continent: Australia, Germany, Africa, Asia.
Sir, today actually there are speakers from 5 different continents: Asia, Europe, Australia, Africa, and America. So the speakers from all over the world are presenting talks today. So it's a great pleasure for us and for all the participants also. Thank you.
Thank you.
Yeah, thank you, Dr. Sharma.
Thank you, Dr. Patrick.
Thank you, Dr. Patrick.
Thank you, everybody. Yeah, it was a great opportunity. Thank you so much. Yeah.
Okay, so we will meet at 4 p.m. sharp.
Right. Thank you.
Thank you. Cheers now.
Thank you.
Bye now.
So we are going to meeting close now.